The most alarming scenario that can be imagined regarding the three Atlas objects initially seems like complete madness and incredible improbability. However, upon deeper reflection, a question arises. What if things are not as they appear on the surface? What if this object has no intention of leaving our system at all, and its flyby trajectory is not merely a random or natural path, but a carefully planned maneuver executed with the help of technologies that remain inaccessible and elusive to us at this moment? Imagine that within our universe exists an intelligence so advanced that its technology allows it to create illusions, disguising its ships as meteors, asteroids, or even space debris. These technologies could be so sophisticated that we are simply unable to detect or understand them. The unprecedented speed at which this object moves, along with its chemical composition, seemingly impossible by modern standards, could very well indicate not alien life forms or civilizations, but intentions that have nothing to do with exploration or contact. The closer it approaches perihelion, the point of its closest approach to our Sun, the more hidden systems and mechanisms activate within this object, as if it is preparing for some next phase of a mission that brought it here. Tonight, we will venture into a world of hypotheses and theories where classical explanations no longer hold up to scrutiny, and cosmic paranoia and speculation begin to seize minds. The question is no longer whether this object will fly away or stay, but whether we can recognize the signs of its intentions when it decides to remain or linger. Primarily, the issue is whether this object poses a potential threat or not. So, let's start with the first question. Is the 3 Atlas a real threat to our planet? On July 1, 2025, the Atlas telescope located in Chile detected something unusual. On its screens appeared a bright, glowing spot following a hyperbolic trajectory, which in itself already indicated the unusual nature of the situation. Such a path could only mean one thing. This object arrived from the depths of interstellar space, from another system, and was designated as 3 Atlas, which in formal notation stands for C2025. It became the third confirmed interstellar object discovered after Oumuamua in 2017 and Borisov in 2019. But what if this new visitor carries consequences that significantly surpass all previous assumptions in their nature and scale? What if it is not just another interstellar rock or icy crystal, but something far more mysterious and dangerous? Unlike objects associated with our solar system, which move along elliptical orbits, this object, dubbed the 3 Atlas, is traveling along a hyperbolic trajectory, meaning it is on a path that indicates its ultimate escape from the gravitational influence of our Sun. Its orbital eccentricity exceeds 1, signifying that it has completely left the bounds of regular orbital paths and suggesting that it is moving at such a speed that it will soon leave our system forever. It is rapidly approaching from the constellation Lyra, and its velocity is increasing with each moment, reaching unprecedented levels. Between October 29 and its closest approach to the Sun, expected around mid-November, it will attain speeds of over 130 miles per hour, enough to cross the entire territory of the United States in less than 3 minutes. Yet, despite these impressive figures and mathematical calculations, an important question remains. What if the danger does not lie in its path or speed, but in what it might reveal about ourselves? What if, as it approaches our planet, it has the potential to uncover and expose hidden aspects of human civilization, our technologies, our culture, or even our weaknesses? In early August, the James Webb Space Telescope recorded spectral characteristics that instantly drew the attention of scientists worldwide. These spectra showed unusually high concentrations of carbon dioxide, which in itself is a rare phenomenon in the studied regions of space. However, what was even more astonishing was that this chemical signature indicated formation conditions significantly different from those observed in our solar system. Interestingly, this is not just about a new or unusual characteristic but about a potential mystery that challenges our conventional understanding of cosmic objects and their origins. This anomaly prompts reflection. What if the true significance of this discovery lies not only in what we see but also in what it teaches us? What if it is not merely a puzzle to solve but a signal that we are about to encounter something previously beyond the scope of our knowledge and understanding? Supporting this, observatories around the world have activated their latest radio and optical systems to verify and confirm the initial data. Radio telescopes across different parts of the globe have detected only natural radio waves, the very silence that should have indicated the presence of artificial signals if the object were some technological achievement of extraterrestrial civilizations. This coordinated, multifaceted approach is a prime example of modern astronomy in its most effective and precise form. Global telescope networks have confirmed not only the interstellar origin of this mysterious object but also its trajectory, which, according to the data received, is safe for Earth and poses no threat. However, an important question arises. What will happen when we begin to consider not only safety concerns but also go beyond the usual scenarios, exploring the boundaries of harmlessness? What if these boundaries are merely an illusion, and behind them lie situations that challenge our fundamental notions of humanity's place in the universe? The discovery of such objects suggests that space is far more complex than we have traditionally believed. It is filled with ancient satellites, debris, and remnants of planetary systems ejected into interstellar space as a result of gravitational cataclysms or collisions. These fragments, wandering through space for billions of years, serve as evidence of processes that occurred during the distant epochs of star and planet formation. Each one, like a traveler through time, reveals new facets of a galaxy beyond the influence of our Sun, although none of these objects pose a threat to Earth's safety. And if it turns out that there are many more such ancient interstellar visitors in space than we previously thought, what will be our response? What will happen when we start to formulate hypotheses that go beyond mainstream scientific perspectives and allow ourselves to imagine scenarios that once seemed impossible? In this context, the importance is underscored by The Guardian, which notes that such discoveries are not a cause for panic or apocalyptic scenarios but a reminder that we live in a universe that is much stranger and more interconnected than it appears in everyday life. The detection of such an ancient visitor is not only a reason for scientific reflection but also a unique window into the deep history of the galaxy we inhabit. These objects carry secrets of stellar neighborhoods that we can hardly imagine because their origins date back to the most distant epochs of cosmic formation. What if the entire mystery lies not only in what they can tell us about the past but also in what they can reveal about the nature of interstellar objects in general? Perhaps these messengers are the key to understanding what lies beyond the boundaries of our current knowledge, and hypothetical scenarios we can only imagine with the help of modern telescopes will open new horizons for us. 3 interstellar objects moving through space demonstrate remarkably different speeds, with one, tentatively called the 3-liter drop, moving almost twice as fast as the others. Such sudden acceleration or the presence of strong outbursts from its formation system prompts deep reflection. Perhaps this is evidence that extreme processes were occurring within this body, or that its acceleration was achieved through numerous gravitational interactions during its long and complex journey through interstellar space. But what if such a progressive increase in speed among several interstellar visitors is not a coincidence, but something more? Could it be a hint at the existence of a purposeful, deliberate program or process that guides these bodies along specific trajectories, beyond mere cosmic chaos? Then the question arises: is everything happening here more significant than a random collision of celestial objects? Something that prompts us to consider possible reasons and purposes behind their appearance? Determining the exact size of this body proved to be a challenging task. The complexity lies in its brightly shining comet, which conceals its core, shrouding it in a fog of mystery. Modern estimates of its diameter range from 3 to 6 kilometers, roughly comparable to 3 football fields or a small mountain. This wide uncertainty is due to assumptions about its surface reflectivity, the efficiency of sunlight reflection, and the comet's formation characteristics. Some experts lean towards smaller estimates, as typical comet parameters often suggest such sizes. Even at the minimum estimate of 3 kilometers, we are talking about a sufficiently large object capable of surprising with its significance in the context of interstellar bodies. But what if this very uncertainty in measurements conceals something more profound, beyond the question of mere size? Perhaps within this ambiguity lie the keys to understanding its survival, its ability to withstand the cosmic violence it has endured for millions or even billions of years in the lifeless void of interstellar space. Small objects, as is well known, are far more vulnerable to destructive tidal forces and high-velocity collisions with cosmic debris. Nevertheless, if we assume that such an object managed not only to survive but also to persist for such a long time, it opens the door to speculation about its special properties, its possible unusual strength, its deliberate design, or even hidden protective mechanisms. Maybe this mysterious object is not just a random visitor, but a testament to the existence of mechanisms that allow it to traverse space despite all threats and maintain its integrity. This raises crucial questions about its origin, its longevity, and the role it might have played in the history of the galaxy. The most astonishing aspect is the presumed ancientness of this interstellar traveler. Analysis suggests that it most likely originated in the dense disk of our galaxy during a period when star systems were forming more actively, and the Milky Way itself was much younger and more chaotic. If this is true, then this object could have appeared long before the formation of our solar system, predating it by billions of years, and possibly containing within itself recorded layers of galactic evolution, information about how the universe developed in those distant times when galaxies were significantly smaller and less organized. This raises the question, could this ancient origin story be the key to new, deeper speculations that challenge our conventional perception of time, the purpose of existence, and even intelligent life forms capable of interstellar travel? The position of this object relative to the galaxy's rotation suggests that it moves along an unusual orbit, different from most. The same hyperbolic trajectory that defines this interstellar object as a unique visitor from the depths of space also serves as a guarantee of its safe passage past our Sun. Its velocity is so high that it cannot be captured by our star's gravity or become its satellite. The minimum distance from the planets of the solar system is measured not in kilometers but in astronomical units, distances that easily convey that the object poses no threat to our celestial bodies. However, when we begin to consider scenarios beyond scientific calculations, a question arises. What if the worst-case hypothetical situations are not related to physical collision, but rather to the kind of image or meaning this visitor might have in our universe? The observational windows through which we attempt to monitor its approach become complex challenges, as its peak brightness reaches approximately 11th magnitude, requiring powerful telescopes even under ideal observing conditions. During its closest approach to the Sun, the object disappears from view, immersed in the bright glare of our star, precisely when its activity peaks, an almost unfairly random and unpredictable moment. But what if it is this invisibility, linked to the limitations of our observations, that opens the door to the most fantastic hypotheses, where what we cannot see or measure is more important and significant than what we can detect? In this case, an image emerges, a portrait of cosmic resilience, ancient, swift, and fleeting, that combines physics and risk, reminding us that the universe operates on scales beyond any of our experience, following laws precise enough to predict this visitor's position for many years to come. However, when we dare to ask what lies behind these predictable trajectories, what hypothetical worst-case scenarios might occur, unrelated to orbital mechanics, we enter the realm of cosmic revelations. This is Part 3, Chemistry in Silence. When the James Webb Space Telescope's infrared view scanned the object designated as Tri-ATCs on August 6, it discovered something truly extraordinary. A comet dominated by carbon dioxide, with the ratio of CO2 to water approximately 8:1. Such a discovery went beyond conventional notions of comet chemical composition and became unprecedented in the history of astronomy. But to go beyond pure chemical analysis and ponder deeper meanings, the question arises: what if this molecular signature is not merely a coincidence, not the result of natural processes, but a hint at purposes or origins that extend far beyond typical comet formation scenarios? Usually, comets follow predictable paths. Their water ice sublimates at moderate temperatures, forming characteristic clouds of water vapor and dust. Then carbon monoxide appears, followed later by carbon dioxide, indicating ongoing processes within their composition. Molecular ratios tell us about the conditions of their birth and subsequent evolution. However, tri-ATCs completely rewrote this familiar story, highlighting carbon dioxide as a product arising from industrial processes rather than natural origins. And what if this deviation from the norm is not just a rare anomaly but a key to new hypotheses challenging our understanding of the nature and origin of such bodies? These figures become especially striking considering the distance to the object. When the James Webb Space Telescope detected the spectrum of this cometary body, it was more than 3 astronomical units from the Sun, significantly beyond Mars' orbit, emphasizing its remoteness and the difficulty of observations. Most comets typically exhibit only weak activity when far from the Sun, with their coma usually barely noticeable, often consisting of a thin veil of gas and dust. However, this unusual object surprised scientists because its coma, mainly composed of carbon dioxide molecules, extended hundreds of thousands of kilometers into space around the nucleus, making its activity detectable even at considerable distances. What could have caused such unusual activity? If we suppose that this phenomenon, rare and inexplicable within standard models, begins to be considered as a possible basis for hypotheses about energy sources, internal mechanisms, or even purposes that go beyond our current understanding of nature, then a whole spectrum of speculative scenarios opens before us. Several hypotheses attempt to explain this phenomenon. The first hypothesis suggests that such an object could have formed near the snowline, an area rich in carbon dioxide, where molecules of CO2 preferentially condensed in the protoplanetary disk, allowing it to preserve this unique chemical structure. The second hypothesis proposes that the object's extreme age and prolonged exposure to cosmic rays could have radically altered its surface chemical composition. Radiation processing may have created thin layers that insulate the water inside the comet while simultaneously allowing carbon dioxide gas to escape freely. The third version posits that this body possesses a kind of dust mantle developed over billions of years, functioning as a cosmic insulator that prevents water from escaping but permits more volatile gases, such as carbon dioxide, to penetrate outward, forming a sort of barrier system. However, what if all these natural explanations, despite their seeming plausibility, do not reveal the most troubling and significant possibility? What if the chemical signature of this object, its molecular fingerprint, is more than just the result of natural processes? It is a consciously constructed signal, a message or indicator created for purposes we have yet to understand. Modern tools, such as the Webb Near-Infrared Spectrometer, enable the detection of molecular fingerprints with high precision, capturing molecules emitted when the coma is heated by sunlight. These emissions occur at specific wavelengths, allowing scientists to determine the comet's chemical composition. To their surprise, the observed ratio of molecules in this coma, approximately 8:1, is one of the most extreme cases of increased carbon dioxide content ever recorded in comet observations. And if we go beyond simple spectroscopic data and begin to ponder the meaning of this unusual ratio, a question arises. What if these molecular signatures are not merely chemical anomalies but messages containing information that far exceeds conventional science? Perhaps they encode messages or point to objectives that challenge our usual notions of intelligence capable of cosmic cooperation or communication. This is not entirely a new phenomenon in astronomy. For example, Comet C. 2016 R2, Pan-STARRS, also exhibited unusual ratios of volatile substances, with an extraordinarily high content of carbon monoxide and nitrogen. Such chemical anomalies suggest either that comet formation processes can be far more diverse and complex than previously thought or that dramatic changes occurred after their formation, significantly altering the surface's chemical composition. When we begin to examine these phenomena within the framework of hypotheses, it appears that the presence of such chemical anomalies in numerous objects may indicate underlying patterns, signals that highlight their possible extraterrestrial origin or, at the very least, suggest processes that go beyond natural scenarios. The significance of this so-called atlas is profound. When we start contemplating the possibility of ancient intelligent systems capable of encoding and transmitting information through the very structure of chemical compounds, a series of speculative scenarios emerge that demand careful consideration. Modern observations of cosmic objects allow us to understand whether the phenomena observed are predominantly related to surface saturation with substances or, conversely, are surface manifestations hiding deeper layers. As solar heating increases, especially in cases where molecular balances may shift, such as when water ice lies beneath saturated carbon dioxide surfaces, there arises an opportunity to determine how deeply these objects' internal layers are embedded within their composition. Changes in thermal penetration can provide clues about what lies beneath the surface layer. What if, as the objects approach perihelion, the closest point to the Sun, the chemical signatures begin to exhibit patterns inconsistent with simple heating? Could these changes indicate not random processes but systematic activation, awakening ancient systems or structures that have long remained dormant? Such a scenario opens the door to speculation about the existence of dormant systems that are activated by solar heat, awakening long-forgotten mechanisms or even traces of intelligent technologies embedded in their chemical makeup. This mysterious chemical history extends beyond specific observations of the three studied objects and transforms into a universal hypothesis. If interstellar bodies demonstrate a regular presence of unusual and even exotic compositions, it can be hypothesized that planetary formation processes around other stars have led to a broader diversity of icy and rocky bodies than we observe in our own system. As a result, the richness and complexity of their chemical compositions may reflect various conditions that existed during the early stages of planetary system formation or indicate different stages of their evolution. Samples similar to those found in the three atlases may not be unique but could represent only a part of a broader scenario characteristic of certain types of stars or specific phases of such systems' development. But as we approach the boundaries of scientific hypothesis and begin to question deeper causes, a thought arises. What if these exotic chemical components are not accidental or the result of random processes, but deliberate traces, markers, or signatures indicating the presence of intelligent civilizations inhabiting the cosmos? What if these chemical anomalies are not merely incidental traces of natural processes, but signs of activity created by intelligent beings who have left their mark within the composition of interstellar bodies? In other words, perhaps we are starting to detect the first signs of cosmic intelligence manifesting through chemical traces left in interstellar objects, and these signatures could become keys to understanding that we are not alone, that there is something greater than mere random collisions and planet formation in the vast expanses of the universe. Expanding our perspective, one could say that this unusual chemistry serves as a kind of testing ground for models of planet formation and the evolution of icy and rocky bodies beyond our solar system. If the theories explaining the origin and development of icy objects are correct, then they should be capable of accounting for the rich and diverse array of interstellar visitors that periodically come to us. However, these observations challenge our current expectations, pointing either to gaps in our theories or to the existence of vast ranges of conditions present in different parts of the galaxy, about which we still know nothing. As a result, our understanding of the formation and evolution of interstellar bodies needs revision, and potential anomalies and unexpected discoveries compel us to consider more complex and diverse scenarios. When we go beyond conventional theoretical frameworks and begin to speculate purely hypothetically, the distance separating our Earth from Mars during their closest approach exceeds twice that distance and generally amounts to more than 50 times. At the same time, this distance is nearly equal to the separation between our planet and the Moon. Astronomers report that the most probable time for this close approach is around October 29, when the object known as perigee is approximately 0.04 astronomical units from the Sun. This position places it between Earth's and Mars's orbits, which, overall, is close enough to significantly heat it with solar rays and cause an impressive outflow of cometary material from a region known as the Sodvos. However, in reality, this distance is not so small as to influence planetary orbits or cause debris from this object to fall onto any planet. Nevertheless, when we begin to consider hypothetical scenarios where distance no longer seems critical, for example, in cases involving advanced technologies, intelligence, or objectives beyond simple physical proximity, the importance of such assessments changes. In these situations, we cannot rely solely on simple approximations or rough estimates based on basic celestial mechanics. Precise orbital calculations are necessary, taking into account not only the primary gravitational influences of planets but also the effects of relativistic shifts and minor perturbations caused by radiation pressure or solar wind. When astronomers state that an object known as the 3 Atlas does not pose a threat to Earth, this conclusion is based on a deep understanding of centuries of observations, accurate models, and decades of tracking potentially hazardous celestial bodies. These assertions are supported by confidence that all calculations are grounded in proven and tested celestial mechanics, which has demonstrated its reliability over many years. However, what happens if these same calculations, serving as our guarantee of physical safety, are in the future used to construct speculative, often grim scenarios that, in essence, have nothing to do with an actual collision? Imagine that we are not talking about physical destruction or catastrophe, but about contact, communication, or even a cosmic revelation. And what if the speed at which an object moves, more than 30 miles per hour, actually turns out to be our ally rather than a threat? Objects traveling along hyperbolic trajectories at such speeds cannot be captured by the sun's gravity. Their paths are so rapid and unconventional that they pass by without lingering in the system, disappearing into interstellar space even faster. This raises the question, what if such incredible speed and the inability to capture are not merely the result of natural physical processes but something greater? Perhaps hidden behind this is an unprecedented, deliberate design, carefully timed and targeted objectives far beyond our current capacity for detection or understanding. This scenario emphasizes the importance of distinguishing between official communication and actual risks. At first glance, an interstellar object evokes an emotional response. Its presence seems mysterious and unsettling, but at the same time, its ability to travel at such speeds along a hyperbolic trajectory indicates that it does not pose an immediate danger to our planet. Our knowledge of the scale of the cosmos and orbital mechanics allows us to perceive such encounters more as exciting than frightening events. However, if we focus too much on the potential physical threat, we may overlook other, deeper, and more hidden risks. For example, the risks associated with such objects potentially revealing more about us than we are prepared to disclose. Our assumptions, our place in the universe, our technologies and capabilities. All of this could become the subject of astonishing and even unsettling revelations. When it comes to communications from NASA and other space agencies, it is important to maintain a balance between scientific honesty and clarity on one hand, and avoiding unnecessary alarm on the other. The recent interstellar objects that visited our solar system provide us with crucial context for understanding these mysterious bodies. In 2017, when an unusual object, named Oumuamua, first entered Earth's orbit, it posed no threat. Despite its unusual and quite enigmatic behavior, astronomers regarded it more as a rare but natural phenomenon, not cause for concern. At the time Oumuamua was passing by, observations indicated that its activity was relatively predictable, and its trajectory was typical for such interstellar passages. In 2019, another interstellar object known as Borisov exhibited the same predictable cometary activity, further confirming this trend. These two examples began shaping the perception of a series of such visitors, which scientists tentatively refer to as the 3 Atlases, a series of interstellar bodies displaying similar characteristics. They are energy active, follow unconventional trajectories, and seemingly do not pose a threat to Earth. However, despite their appearance as simple cosmic visitors, researchers are starting to wonder, what if behind this apparent harmlessness lies something far more significant and mysterious? Perhaps these interstellar travelers are not just natural comets or asteroids but carriers of information about a broader cosmic context, about some universal registry or gradual unveiling of secrets that challenge our current understanding of space, the nature of intelligence, and the goals pursued by extraterrestrial civilizations. All we currently know about them are basic facts, forming a solid foundation for further reflection. We have data on their speeds, trajectories, and unusual composition, which is rich in carbon dioxide. Evidence suggests that these objects originate from ancient star systems, possibly from dense regions of the galactic disk, from which they were ejected or torn away. Modern telescopes, among the best in the world, allow scientists to conduct detailed analyses of their chemical makeup, physical behavior, and dynamics. All these data paint a picture: ancient, fast-moving bodies that, in their characteristics, resemble chemically unusual but natural comets. Yet, behind these promising conclusions lies a profound and still unresolved unknown. What speculative scenarios might arise if we consider not only the nature of these objects but also the roles they could play in a universe where intelligence can take forms beyond our comprehension? The most pressing questions remain regarding their sizes and origins. Precise estimates of their nuclei range from a few hundred meters to several kilometers, and explanations for the dominant presence of carbon dioxide in their surface composition and volume continue to spark debate and remain unclear. We cannot definitively identify the parent star systems from which they originated, nor can we reconstruct the exact sequences of gravitational encounters that may have shaped their current trajectories. However, it is important to emphasize that all these unknowns do not affect the current risk assessments for Earth and humanity. They are more a basis for contemplating hypotheses beyond standard natural explanations. This approach exemplifies the correct way to evaluate potential astronomical threats, distinguishing scientific curiosity from concerns about actual danger. Public and media coverage of this issue generally reflected a mature understanding of the situation, highlighting both the scientific value of studying such objects and their harmlessness. Visual evidence obtained with the best modern instruments tells consistent stories. Images captured by the Hubble telescope display classic signs of cometary bodies, such as tails, and this confirmation of universality is one of the most profound and significant discoveries in contemporary astronomy. It demonstrates that even the worst-case scenarios, based on measurable physical threats to our planet, are completely refuted. The mathematical models we used to analyze this phenomenon remain clear and definitive, and the observations conducted systematically and carefully support conclusions that inspire hope and confidence. This cosmic visitor, whether it came in peace, intentionally or by accident, represents more than just an object in our celestial space. There comes a time when we, consciously or not, cross the boundaries of conventional scientific dogma and enter the realm of pure speculation, an area where the worst scenarios take on forms unrelated to threats to our physical existence, but rather challenge our understanding of what is possible in the universe. This universe may be far more populated, far more intelligent, and far more purposeful than our current models and theories suggest. Part 3. Alien Technologies or a Comet. Now we consciously move from the realm of established facts into the sphere of hypotheses and conjectures, where possibilities expand like reflections in an infinite hall of mirrors. All that follows should be regarded as a thought experiment, a journey into the world of hypotheses rather than definitive scientific conclusions. It is an attempt to imagine hypothetical scenarios separate from what we truly know and confirm. To date, as research shows, most evidence indicates that the object known as Triatlas is a natural celestial body, a comet. However, let us still consider what this might mean if, in the future, our understanding proves incomplete or even mistaken. The basic and most consistently supported position remains unchanged. Leading astronomical organizations such as NASA, the European Space Agency, and virtually all major institutions involved in astronomy describe Triatlas as a natural cometary visitor. This is not the result of bureaucratic conservatism or groupthink, but a conclusion based on current data, which confirms that the object exhibits behavior typical of comets. It follows predictable orbits governed by the laws of mechanics, and its spectroscopic signature shows signs of ice sublimation, standard cometary features. Viewing this as a natural phenomenon is reinforced by the so-called Occam's razor, the principle of minimizing assumptions, which suggests that the simplest explanation is often the correct one. However, as in any science, we must remember that history is full of unexpected discoveries. Many of the most important and significant findings have been made thanks to objects initially seeming ordinary and unremarkable. For example, pulsars were first discovered as mysterious radio signals so regular that they were even called little green men, LGM, until it was revealed that they are rotating neutron stars. Fast radio bursts, which long puzzled astronomers, ultimately turned out to be signatures of exotic and unusual cosmic processes. Perhaps Triatlas is no exception, and nature will surprise us once again, proving that the universe is far stranger and more wondrous than we have assumed. Speculations about the possible artificial origin of the object do not arise out of nowhere. Astrophysicist from Harvard University, known as Avalope, who previously drew attention to his unconventional interpretations of Oumuamua, has already begun to express hypotheses in various interviews and blogs suggesting that such an object might have an artificial origin. Although these ideas remain on the fringe of scientific hypothesis, they generate interest and prompt us to reconsider our understanding of the nature of such phenomena. Loeb's position, which is clearly stated as his personal opinion rather than an established scientific fact, suggests the need to remain open to the possibility that some interstellar objects may not be natural phenomena at all, but could instead be artificial structures or technologies created by extraterrestrial civilizations. This viewpoint warrants serious and thoughtful consideration, not because it is necessarily supported by evidence, but because it serves as an example of how to approach unusual claims and hypotheses. First and foremost, it is important to understand what observations or signs could serve as convincing evidence of an artificial origin of an object, and which, on the contrary, would lead us to reject the hypothesis of a natural comet in favor of more exotic scenarios. These questions are extremely important, as they help us draw a fine line between healthy scientific skepticism and unwarranted rejection of ideas that initially seem unusual or extraordinary. In the case that the 3 Atlas truly is an artificial structure rather than a natural object, it should exhibit characteristic signatures that distinguish it from ordinary celestial bodies. For example, we might expect the presence of coherent radio emissions indicating onboard electronics or communication systems embedded within the structure. Such signals should be clearly artificial in origin, not just random electromagnetic noise typical of natural bodies. An additional key indicator could be unusual acceleration patterns that cannot be explained by simple gravitational effects or sublimation of gases. Natural comets often show slight deviations from purely gravitational trajectories because gases escaping from their surfaces create microscopic thrust forces. However, if the 3 Atlas changed its velocity or trajectory to an extent that could not be explained by gas emission or solar heating, this could suggest the presence of some propulsion or control systems. Engineering features such as light curves, changes in brightness over time, are also important. By analyzing these curves, scientists can gain additional clues about the nature of the object. Natural comets typically exhibit predictable increases in brightness as they approach the Sun, often with variations related to rotation, surface heterogeneity, or patterns of gas emission. In the case of an artificial object, brightness variations might follow different, more controlled patterns, possibly related to changes in orientation or activity of control systems. To date, none of the proposed signs of artificial origin have been observed in the 3 Atlas. Radio observations conducted by radioscopes have only recorded the absence of signals or manifestations indicating activity, as well as the presence of natural emissions characteristic of sublimating cometary materials. Its trajectory through interstellar space is entirely governed by the laws of celestial mechanics and shows no unexplained deviations. Variations in the brightness of this object correspond to typical patterns observed in other comets when they rotate and respond to solar heat. Regarding its chemical composition, the dominance of carbon dioxide, although it makes this object chemically unusual, does not in itself serve as evidence of artificial origin. As we have previously discussed, there are many natural processes capable of producing a high carbon dioxide content in a comet. For example, surface processing by radiation or solar radiation can alter chemical composition, the formation of CO2 near snowlines in protoplanetary disks, or the development of insulating dust mantles, all of which could explain the elevated carbon dioxide levels without the need to assume artificial origin. Thus, to date, all observed features of the object fit within the framework of natural cosmic phenomena. No clear signs have been found in its behavior, trajectory, or chemical composition that would indicate an artificial, technological nature. Nevertheless, it remains important to remain cautious. Moving from the idea of a chemically unusual object to the hypothesis of its artificial origin requires convincing evidence that no natural processes can account for the observed characteristics. This is where the lessons learned from the study of Oumuamua are crucial, the first confirmed interstellar object to visit our solar system. This unique cosmic visitor sparked a flurry of speculation about its possible artificial origin, especially due to its unusual elongated shape and the noticeable slight acceleration observed during the observations. In response, radio telescopes and other instruments conducted extensive and systematic searches for artificial signals, but no signs were found. A careful analysis of the comet's motion showed that the observed non-gravitational forces could be explained by the outgassing of water ice, which in turn indicates a natural mechanism for its behavior. Therefore, what initially seemed extremely unusual and even exotic was ultimately explained within the framework of natural processes, confirming the importance of a cautious and critical approach in scientific research. This model suggests that when evaluating hypotheses of artificial origin, it is essential to remain open to unusual possibilities while strictly demanding convincing evidence. The scientific method is effective precisely because it applies equally rigorous standards to any hypothesis, whether ordinary or extraordinary. Claims of potential artificial origin must meet these criteria and should not be based solely on gaps or shortcomings in our current knowledge. Responsible discussion of such hypotheses should be accompanied by clear labeling and proper context to avoid misleading conclusions. For example, when mass media discuss the possibility of an artificial origin for certain interstellar objects, they should explicitly state that these are speculations rather than confirmed scientific hypotheses. This distinction is important not only within the scientific community but also influences public perception of both the specific object and the entire scientific process. In this sense, speculation serves an important function. It goes beyond mere entertainment or sensationalism, encouraging the scientific community to think more deeply and comprehensively about what differentiates natural phenomena from potential artificial ones in space. Discussing the hypothesis of a possible artificial origin of a comet prompts scientists to develop new observational tests that could, in theory, disprove the idea of its natural origin. This serves as a reminder that the universe may still hold unexpected surprises that challenge our current understanding and knowledge. In the future, we will continue to observe such objects to test these speculative scenarios. For instance, additional spectroscopic studies, especially as the comet approaches perihelion, could reveal chemical signatures difficult to explain within known natural processes. Precise astrometric measurements might detect anomalies in the trajectory indicating possible controlled movement or influence from artificial mechanisms. Long-term monitoring of the comet's behavior could uncover patterns that cannot be explained by passive cometary activity alone, becoming a crucial argument in the debate over its nature. However, the burden of proof remains on those proposing an artificial origin hypothesis, as convincing and unequivocal evidence must be provided to refute the existing scientific consensus. The hypothesis of a natural origin for the comet has a significant advantage because it aligns with established physics, typical comet characteristics, and observed behaviors of similar interstellar objects that have previously visited our system. To disprove this scientific standard, evidence must clearly demonstrate the inadequacy of natural explanations while simultaneously supporting the possibility of an artificial origin for this celestial body. Reflections on the possibilities related to the origin and nature of mysterious objects represent an important intellectual exercise that helps broaden our horizons and stimulates the imagination. However, such mental exercises should not distract us from the wonderful and truly fascinating reality that is actually represented by three atlases. These ancient and enigmatic celestial bodies are not merely random visitors in our galaxy. They are like small comets carrying unique information about those inaccessible regions of space, about environments we have never had the opportunity to explore. Within their chemical composition and structure, there may be clues about processes that occurred billions of years ago, about events that shaped the development of our galaxy and left traces in the cosmic space, making them true carriers of deep history. These objects do not require complex or exotic explanations. Their very existence is already sufficiently astonishing and mysterious. The more we examine these ancient atlases, the clearer it becomes that they are not just astronomical artifacts but keys to unlocking our cosmic roots and history. As we delve into this speculative journey, it is important to remember that the most significant discoveries in astronomy often occurred thanks to patient and meticulous observational approaches. We should not forget that mysterious phenomena such as pulsars, quasars, gamma-ray bursts, and gravitational waves were once perceived as enigmatic signals that raised questions and confusion. Yet, it was precisely these mysterious phenomena, through the perseverance and careful study of scientists, that ultimately revealed new laws of physics and allowed us to understand much more about the nature of the universe. Today, a question arises: could the hypothesis of 3 asteroids, designated as the 3 ices, ultimately turn out to be just another comet from interstellar space, or will it reveal something far more unusual and astonishing? Already, these objects have expanded our understanding of interstellar space and the diversity of objects that move freely between stars, like wanderers leaving behind their mysterious traces. The next stage of our speculative exploration will immerse us in even more dramatic scenarios, not because they seem probable, but because they help us pose important questions and understand the limits of our knowledge. When we encounter something unprecedented, the boundaries of our ordinary imagination and possibilities expand. These mental experiments serve as a kind of bridge between what we know and what remains beyond our current understanding. In them, we strive to clearly distinguish between speculation and facts, between revelations that can be confirmed and hypotheses that remain at the level of hypothetical conjecture. They help us understand how our perception and knowledge can change when faced with new, sometimes shocking, possibilities. Part 6 is dedicated to one of the most intriguing and, at the same time, most ominous scenarios: the so-called dark forest. In this case, we delve into the very depths of our fantasies and assumptions, where the shadows of cosmic possibilities stretch out and create scenarios capable of fundamentally altering our perception of our place in the universe. Everything that follows is merely a mental experiment, an attempt to imagine the consequences and potential implications of such hypothetical situations. They are not confirmed by current scientific data and lack practical verification. However, they serve as important illustrations of profound questions that could arise if our assumptions about space turn out to be incorrect. If the hypothesis about 3 asteroids, tentatively called 3 ice, proves insufficient to explain their nature, then the idea of the dark forest emerges both from science fiction and serious discussions within scientific circles. The name of this concept is borrowed from a scenario where our solar system becomes the subject of close study by intelligent beings possessing truly fantastic technological capabilities. These beings are capable of creating complex devices and systems that can withstand billions of years of travel through interstellar space, remaining virtually undetectable to us, manifesting only as natural phenomena. Their mastery of camouflage and invisibility indicates a technological level far surpassing our current achievements in science and engineering. To understand what requirements such a hypothetical mission must meet, one must carefully imagine the engineering and technological aspects that would enable the realization of such a scenario. For example, a probe designed to imitate a natural cometary body would need to reproduce all the nuances of real comets' behavior. It should emit spectral signatures that precisely match the models of gas release during heating by solar rays, allowing it to blend with natural objects and avoid suspicion. The surface of this device should reflect light in a way that its appearance fully corresponds to the properties of ice and rock typical of comets, taking into account the light transmission and reflection characteristics inherent to these materials. Inside, the probe would need to contain enough volatile substances to maintain its disguise throughout its passage through the solar system. To achieve this, it would be necessary to equip it with sensors, processors, and communication systems that justify such a complex mission. And all of this undoubtedly requires enormous energy resources. The power requirements for such systems would have to be truly colossal. Maintaining active systems over interstellar distances for billions of years would demand energy sources vastly exceeding our current capabilities. Perhaps radioisotope thermoelectric generators, devices capable of providing power for millennia by converting the heat from radioactive materials, were used. Alternatively, advanced thermonuclear fusion reactors, operating on interstellar hydrogen, might have supplied the necessary level of energy. It is also possible that these devices could draw energy from cosmic rays or interact with magnetic fields during their journeys, constantly replenishing their energy reserves. If needed, one might imagine that these entities utilize unique mechanisms to harvest energy from their environment, enabling them to sustain operations across entire billions of years. Let us, within this speculative framework, suppose that our observations of the solar system have achieved certain successes and have begun to detect signs that cannot be explained by natural processes. Radio telescopes register brief signals with structured and organized characteristics when an object crosses the boundaries of our system. Its trajectory shows minor but consistent course corrections, indicating active control and navigation. Or perhaps the chemical emissions from this object reveal complex and organized chemical patterns that would be difficult to explain through random processes such as sublimation or natural reactions. At this point, a question arises. What should humanity do when signs of such unusual activity are detected? The most dramatic and significant developments could occur when our monitoring systems start to record not just one, but an entire network of secondary objects detaching from the main body. These smaller probes could be stationed at various points within the solar system to ensure long-term observation and control. One might orbit around Venus, another around Mars, and others could be placed in the asteroid belt or in gravitationally stable Lagrange points. As a result, the entire solar system would transform into a branching network of numerous devices observing the phenomena and transmitting information about unknown capabilities and the intentions of their creators. This raises an immediate and crucial question. How should our civilization respond when faced with such an unprecedented and potentially threatening situation? This hypothetical scenario would instantly transform into a reality. Unlike the slower and more gradual first contact scenarios often depicted in science fiction, which typically involve a lengthy and complex process of establishing communication with extraterrestrial civilizations, the actual discovery of an active observation system would represent a true breakthrough for humanity, capable of thrusting us into an entirely new reality. This new reality would be permeated with the understanding that intelligent life already exists in our nearby cosmic neighborhood, possessing technologies far more advanced than our own. In such a situation, questions related to managing this discovery would acquire unprecedented urgency and scale. Who exactly has the authority to speak on behalf of Earth? Who should make decisions in the face of such a momentous event? The United Nations, as an international forum designed to unify efforts among nations on issues of common security and cooperation, might find itself unprepared for such a challenge. Beyond that, there are major space agencies and scientific organizations that would need to define their positions at the moment of discovery. An equally important factor is the role of individual countries with advanced capabilities in space technology and reconnaissance, as they may have their own perspectives and interests in this situation. The entire scientific community that first detects the active observation network would face an unexpected complication: achieving a unified, global consensus on the next steps. It is particularly striking how difficult it is to reach unanimity on a matter that goes beyond routine tasks and requires a coordinated strategy among nations and institutions that usually collaborate only on simpler and more predictable issues. Soon after the initial discussions, which at first were purely theoretical and hypothetical, the conversation would shift to practical questions. For a long time, debates have raged within the scientific community about the advisability of sending radio signals into space, as opposed to simply listening to and studying signals from potential extraterrestrial civilizations. Some experts believed that actively announcing our presence could attract unwanted attention from potentially hostile or unfriendly alien entities. They feared that such actions might lead to unpredictable consequences, and that hostile civilizations could interpret our radio signals as a call to aggression or a sign of weakness. Others argued that complete silence and refusal to transmit signals do not guarantee safety. In their view, since any civilization capable of crossing interstellar distances would likely detect our technological signatures regardless of whether we consciously broadcast information about ourselves or not. Speculations regarding our role and the reactions of extraterrestrial intelligences become even more complicated when considering a hypothetical scenario in which the 3 Atlas and its hypothetical secondary probes actively study human civilization. In such a case, our response would itself become part of the collected data. Silence in this context could be interpreted either as a sign of wisdom or as an expression of fear and uncertainty. Attempts to establish contact are another important aspect. Some experts believe that active efforts to communicate could indicate either benevolence and curiosity or hostile intentions and aggression. Internal debates and discussions within scientific and governmental circles about how to respond to the detection of extraterrestrial observation systems will soon escalate into a real crisis situation. Humanity will face complex tasks related to informing the global public that we are being observed by extraterrestrial civilization surveillance systems, while avoiding panic and social chaos. Maintaining scientific objectivity and honesty will be crucial, along with recognizing that the opportunities opening before us go beyond our usual understanding. Additionally, there will be a need to distinguish confirmed observations from speculative interpretations, as the fate of human civilization could be at stake in a critical moment. In an era where information becomes a key resource, the distinction between legitimate scientific observations and unfounded speculation will become an increasingly important criterion in shaping a rational and balanced public dialogue about one of the most significant discoveries in human history. The ability to correctly interpret and assess potential breakthroughs, capable of forever changing our view of the universe, depends on this distinction. The technological implications of such discoveries promise to be no less profound and extensive than the scientific breakthroughs themselves. For example, if the 3 Atlas detects capabilities beyond our current understanding of physical laws, it could open new horizons in engine development, energy generation methods, materials science, and communication technologies. Each of these areas has the potential to lead to revolutionary changes in the technologies used by humanity, fundamentally transforming our daily lives. Such a scientific breakthrough could serve as a catalyst for accelerated development, shortening our progress by centuries, assuming that the intelligence controlling this mysterious object can ensure our survival and further development. However, among all possible scenarios, it is the temporal consequences of such a discovery that evoke the greatest concern. If the 3 Atlas had traveled for billions of years, it would imply that the civilization that created it possesses interstellar capabilities that could differ significantly from what we know today. Perhaps this consciousness has already vanished, leaving behind only automated systems designed to perform tasks originally created by beings long gone before the appearance of our Sun. This hypothesis is unsettling, as it suggests that we are not dealing with active interference from an alien civilization, but rather with the ghost of long-extinct technologies, autonomous systems that continue to operate according to their programmed instructions across endless epochs. These systems may have long since gone beyond the control of their creators and now serve merely as mechanical executors of their initial commands, having no direct connection to living minds. They might carry out their mission with mechanical precision, unaware of their own nature or purpose. Of course, confirming or refuting such scenarios requires constant and vigilant monitoring. Ultimately, none of these speculative scenarios are supported by current astronomical observations. Every newly obtained spectrum, measurement, and image continues to support the hypothesis that the 3 Atlas is a natural interstellar object. Its behavior fully aligns with the predictions of modern astronomical theory regarding the motion and properties of interstellar comets. Its chemical composition, despite being unusual, falls within the range dictated by natural processes occurring throughout the universe. Its trajectory obeys known laws of physics without the need to invoke hypotheses about exotic or unknown forces. The most valuable aspect of this hypothetical exercise is not its likelihood but how quickly and vividly our perception of reality can change if our assumptions about the nature of this object prove to be mistaken. It reminds us that the universe has repeatedly demonstrated its capacity to surprise and challenge our understanding, and will likely do so again. Such experiences highlight the importance of balancing healthy skepticism with openness to new possibilities beyond our current scientific comprehension. As we venture into increasingly subtle and uncertain boundaries of hypotheses, we must remember that we are not exploring an established reality but a spectrum of potential possibilities. The real 3 Atlas is still a natural phenomenon, ancient, rapidly moving, with unusual chemical properties, yet remaining within the framework of existing scientific models. The question of whether our current knowledge is sufficient to fully understand this object remains open. However, future observations and research will sooner or later provide a definitive answer, and that answer will most likely come in the form of compelling evidence allowing us to judge the nature of the 3 Atlas with the cold clarity and precision characteristic of the scientific method. Part 8. Signals of the Great Filter. The concept of this mysterious and profound phenomenon arose from reflections on one of the most fundamental questions ever faced by any civilization that has achieved technological advancement. If the universe should be filled with intelligent beings, then why do we observe no convincing signs of their existence? This philosophical and scientific paradox was first clearly articulated by the eminent physicist Enrico Fermi in the 1950s, which sparked decades of theoretical speculation about the barriers that hinder the emergence, development, and survival of intelligent life, as well as its ability to spread across the galaxy. In the context of our investigation into a hypothetical civilization, referred to as the third party, we confront the possibility that this ancient traveler may not be a mere coincidence but could carry a message from intelligent beings who have encountered insurmountable obstacles of their own. The Great Filter hypothesis suggests that somewhere along the long chain of evolutionary stages, ranging from simple chemical processes to the development of complex civilizations capable of interstellar travel, there exists a critical step so improbable, so difficult, or so dangerous that nearly all attempts to overcome it end in failure. This filter seemingly could manifest at the earliest stages of evolution, for example, during the transition from inanimate matter to self-replicating systems. Or it might appear later, when civilizations develop technologies so powerful that they could destroy themselves before learning to use them wisely. If we assume that this object, designated as the third party, is the result of engineering rather than a natural phenomenon, then the immediate question arises about the fate of its creators. The age of this potential artifact may reach billions of years, indicating its origin from a distant period in our galaxy's history, an era when star systems, chemical compositions, and cosmic conditions differed significantly from today. If this ancient visitor truly is an artificial object, a logical question follows. Has the civilization that created it survived long enough to witness its arrival in our solar system? The timescales involved in this question are almost unimaginable for human perception. The history of human civilization, from the earliest agricultural settlements to the space age, spans roughly 10,000 years, while recorded history accounts for about 5,000 years. Our modern technological civilization has existed for only a few hundred years, yet if we assume that the third party is an artificial object, it could have been functioning for millions of times longer than all of human history. This raises important and profound questions about the duration of technological existence compared to biological survival. Perhaps the most frightening hypothesis is that we may encounter probes that have existed far longer than their creators, who vanished millions of years ago. Such objects, like cosmic messages in bottles, could endlessly drift through the galaxy, carrying information from civilizations that, after solving the problem of interstellar communication, ultimately disappeared or were destroyed. These messages, when viewed as evidence of long-extinct intelligent species, evoke both awe and deep reflection. They demonstrate that some forms of technological legacy can outlast their creators, continuing to exist and transmit information from a distant past, opening unseen horizons of cosmic history and showing that the boundaries between life and technology, time and space, can be far more blurred than they seem. Let us consider the implications of creating technologies capable of remaining functional over incredibly long timescales, exceeding our usual notions of eternity. Historically, our most durable artifacts are the grand monuments of ancient civilizations, pyramids, monumental stone structures, and certain radioactive isotopes that maintain their activity and structure over thousands, sometimes millions, of years. These objects serve as witnesses to past eras and remain resilient over time thanks to the use of natural materials and technologies relevant in ancient times. However, to keep complex electronic systems, moving mechanisms, or artificial intelligence systems operational over billions of years, we would need to develop principles that today seem more hypothetical than achievable. Such principles would include materials that create components more durable than diamonds, as well as energy systems capable of maintaining functionality over periods exceeding the lifespans of most stars, already beyond our current understanding of durability. Equally important is software architecture capable not only of functioning over such scales but also of adapting to changing conditions, self-repairing, and evolving across geological epochs. The success of creating such systems implies that their creators possessed unprecedented technological capabilities and knowledge, which now seem fantastical. Any civilization capable of sending interstellar missions that endure for billions of years would have to solve numerous complex technical challenges that we have not even begun to consider. It should have been capable of understanding the properties of materials at the atomic level, of producing and storing energy on a cosmic scale, as well as processing and preserving information over vast epochs. Such technological capabilities, apparently, should have provided protection against numerous potential scenarios that could serve as obstacles to development, what is often called the Great Filter. However, if we assume that these three atlases are their result, and if this is the only tangible evidence of their existence, a logical question arises. What could have destroyed them despite their incredible technological superiority and capabilities? What forces could have been so powerful that even such civilizations, possessing all these achievements, could not overcome them? One possible explanation is resource depletion on a galactic scale, where their expansion occurred so rapidly and actively that the energy and materials necessary for their existence disappeared. The second hypothesis involves a collision with other intelligent beings who turned out to be hostile, leading to conflicts that destroyed both the aggressor and the victim. An even more troubling prospect is that these civilizations could have fallen victim to internal contradictions inherent in any highly developed society. The capabilities that allowed them to create interstellar probes or carry out large-scale technological projects could also have served as tools of destruction, such as waging wars, causing ecological disasters, or social collapses that proved impossible to control. History offers numerous examples of civilizations that developed technology faster than the wisdom to use it responsibly, and this remains a relevant problem even in our modern world. Humanity currently faces a series of similar challenges related to the danger of misusing its knowledge and technologies. As an alternative to the scenario of complete destruction, there is a hypothesis that the so-called Great Filter may not lead to catastrophic events but rather signify that advanced civilizations undergo evolutionary transformations, making themselves invisible or inaccessible to potential observers. Perhaps, as they develop, such civilizations transition to uploading consciousness into quantum computing systems or merge with their technology so completely that the distinctions between living intelligence and artificial artifacts disappear. There is also a possibility that they ascend to higher dimensions of existence, which remain hidden from our current perception and understanding. In this case, the cosmic perspective necessary for contemplating such possibilities can evoke a sense of dizziness and even awe. Our galaxy, the Milky Way, contains approximately 400 billion stars, many of which formed billions of years before our Sun ignited. These ancient star systems have existed over such vast timescales that it is difficult to even imagine how conditions suitable for the emergence of intelligent civilizations could have developed there. Even if we assume that only a small fraction of these systems gave rise to technological forms of life, it would still take epochs comparable to geological or cosmic timescales to explore and colonize the entire galaxy. Nevertheless, to this day, there is no clear evidence of extraterrestrial civilizations, a phenomenon scientists refer to as the Great Silence. This absence of signatures indicating the presence of alien intelligent beings requires careful explanation and analysis. Modern astronomy and the practice of searching for extraterrestrial civilizations reflect the uncertainty caused by this lack of concrete evidence. Most programs and projects focus on passive listening, monitoring radio signals and other potential signs of alien activity, rather than active transmission, because it is assumed that revealing our presence before fully understanding the galactic environment could be premature or even dangerous. Actively announcing ourselves could attract unwanted attention, which in the context of unknown reactions from other civilizations, presents serious risks. Therefore, until we are certain of the potential consequences, most searches are conducted with great caution. However, once an artificial signature is detected, such as a signal clearly created by intelligence, our current prudence would instantly shift to a state of extreme urgency and alarm. This is why strategic considerations in space exploration and the search for extraterrestrial intelligence are of particular importance. The overarching frameworks and principles developed through this research become especially relevant when considering scenarios related to the so-called Great Filter. This concept suggests that there are difficult stages that civilizations must pass through to avoid extinction, which could explain why we have yet to encounter signs of other intelligent beings. Current astronomical data and observations continue to support hypotheses that attribute the peculiarities of behavior, composition, and development of such systems to natural causes, without resorting to hypotheses of extraterrestrial origin. Speculations about artificial origins or the failures of civilizations remain purely theoretical musings, unconfirmed by facts and more akin to intellectual exercises. However, the importance of these questions is not limited to academic debates alone. They compel us to reflect on fundamental issues of technological development, on the resilience of our civilizations, and on the long-term path we must undertake. If advanced civilizations regularly encounter barriers capable of halting their development or destroying them, that is, if they pass through a great filter, then we must draw valuable lessons from this for our own fate. This concept serves both as a warning and a source of inspiration. It suggests that not only technological capabilities, no matter how impressive, guarantee the successful survival of a civilization. Progress itself introduces new types of risks and dangers that require careful and thoughtful management. At the same time, the idea of the Great Filter motivates us to pursue deeper and more meaningful control over our development. It encourages reflection on how to balance exploratory activities with wise use of technology so that achievements do not become the cause of our own collapse. It also emphasizes the importance of developing solutions that will be more durable than the civilization that created them. In our imagined scenario, the three atlases transform into a kind of cosmic archaeologist. The responsibility that falls on us in the event of discovering evidence of extraterrestrial civilizations would be immense. We would need to learn from the experiences of those who have already achieved significant success in this field, while avoiding the mistakes that led to the destruction of their civilizations, mistakes that are part of the so-called Great Filter. In this context, it is not just a scientific challenge but a matter of the survival of all humankind and the opportunity to realize our potential in outer space, contributing significantly to the dialogue between civilizations and expanding the boundaries of our understanding of the universe. However, all of this remains merely philosophical speculation, hypothetical musings rather than scientific facts. At the same time, the behavior of the so-called three atlases, hypothetical cosmic objects or pathways, continues to be an exact analogy to the behavior of natural comets, following trajectories determined by gravitational and physical laws, not by reason or intentions. The question of whether this understanding is sufficient still remains open, and its final resolution depends on future observations and evidence. As we deepen our exploration into speculative realms, it becomes increasingly clear that the gap between what we imagined and what we actually know is gradually widening. The universe itself already seems astonishing and mysterious, thanks to numerous natural processes, from quantum mechanics to dark energy and large-scale cosmic structures. Adding artificial intelligence to this already extraordinary reality might seem unnecessary to evoke a sense of wonder or to expand our cosmic horizons, which drive all our scientific endeavors. Part 9. The Whisper of Fermi. Where is everything? This question arises after every significant astronomical discovery, lurking behind each search for extraterrestrial intelligence and haunting every moment we peer into the cosmic darkness and encounter only silence. For the first time, this question was posed by Enrico Fermi during an informal lunch conversation in the 1950s. However, as our understanding of the universe has developed, its significance has only grown, acquiring deeper meaning. If we assume that galaxies should be teeming with intelligent beings, if space offers endless possibilities for the emergence and development of life, then a natural question arises. Where is everyone? This paradox, known as the Fermi paradox, takes on new dimensions, especially when we consider interstellar objects such as asteroid and comet fragments, for example, the well-known LC. Each such object, having left the bounds of our solar system, becomes a natural experiment, allowing us to understand how matter propagates through the galaxy and serving as a model for materials and processes occurring around other stars. In theory, these wandering objects should eventually reveal signs of technological civilizations, artificial materials, technological structures, evidence of flooding or constructions that could indicate the presence of intelligent design. However, all detected interstellar visitors so far appeared entirely natural, raising no suspicion of artificial origin. The absence of signs of artificial intervention prompts reflection. What does this say about the nature of advanced civilizations and their interactions with interstellar space? Perhaps truly advanced societies prefer to remain unnoticed, sending so-called silent messengers, if they use probes at all. Such devices are designed to be as indistinguishable as possible from natural objects, stones, meteorites, comets, or asteroids. In this case, the complexity of technological systems, their unique features, distort the possibility of detection, since current search and analysis methods are tuned to recognize obvious artificial signatures. This raises immediate questions about what such signatures might look like and whether it is even possible to detect them in principle. If we entertain the hypothesis that the three ateless objects are indeed something different, then they could undoubtedly be hidden technological objects or probes, concealing their true nature behind the guise of ordinary cosmic comets. Ultimately, it is observational data and their interpretation that can reveal the true essence of this mysterious body. The most crucial difference that helps determine whether an object is natural or artificially created lies in its fundamental behavior and characteristics. This distinction is traditionally associated with the boundary between natural cosmic phenomena and potential manifestations of extraterrestrial technologies. However, this boundary may be much more subtle and complex than we have come to believe, and even more difficult to detect given our current level of knowledge. One of the key diagnostic signs that scientists pay attention to is narrowband radio emissions. Such emissions are the most obvious indicator of technological activity, since natural processes in space generally produce radio noise and broadband signals that are diffuse and difficult to distinguish against the cosmic background. In contrast, artificial transmissions typically concentrate their energy in narrow spectral lines, making them clearly identifiable in spectral analyses. For this reason, for decades, the search for extraterrestrial intelligence has been based on detecting precisely these narrowband, modulated signals, assuming that any civilization capable of interstellar communication would use this method to transmit information. We assumed that such signals should be easily detectable and distinguishable from natural electromagnetic sources. Regarding the object 38-less, its radio telescope observations show that it still only emits electromagnetic signatures characteristic of natural processes. It remains a radiochemist, emitting only signals expected from sublimating cometary material interacting with solar wind and magnetic fields. Specialized observations conducted with networks of radio telescopes have found no signs of coherent signals, modulations, artificial patterns, or other indicators of technological activity. This silence perfectly aligns with the hypothesis of its natural origin. It is simply an ordinary comet moving along a gravitationally determined orbit. However, despite this, we cannot completely rule out the existence of more complex forms of stealth technology capable of masking their activity. Another important diagnostic tool is the thermal profile of the object in the infrared spectrum. In space, natural bodies reach thermal equilibrium with their environment based on well-understood physical laws. They absorb solar radiation, re-emit energy in the infrared range, and maintain a surface temperature determined by their distance from the star, composition, and thermal properties. Artificial objects, on the other hand, may exhibit temperature distributions that violate these natural patterns. For example, the presence of internal heat sources, asymmetric heating, active thermal regulation systems. All of these could indicate conscious control and technological origin. Modern infrared observations, including those conducted with more sensitive instruments, show that the thermal signatures of the object designated as 3ATS are consistent with what is expected from natural cometary materials heated by sunlight. Its surface temperature increases as it approaches the sun, following the inverse square law, which is characteristic of solar heating. The temperature distribution across the surface appears quite random, shaped by topographical features and compositional variations of the comet, rather than by complex thermoregulatory systems typical of artificial objects. If it were an artificial object, its maneuvers and activity, related to controlled thermal management, could serve as the most convincing evidence of its artificial origin. In natural conditions, comets and other celestial bodies follow trajectories determined by gravitational forces. The detection of interstellar objects, such as comets and asteroids, is often associated with their physical characteristics, for example, brightness, which can indicate the size and composition of the body, as well as the rate of gas emission caused by sublimation of surface materials. However, in the case of artificial spacecraft, the situation is fundamentally different. Such devices are capable of performing targeted maneuvers, carefully controlling their course, changing speed, or adjusting their trajectory as needed to achieve specific mission objectives or tasks. These controlled movements require special attention to distinguish them from random or chaotic forces caused by unpredictable asymmetries in gas ejection or natural disturbances. Ultimately, such controlled maneuvers and movement patterns should become noticeable and evident, especially when utilizing modern precise astrometric measurement methods. For example, consider an object designated as a three-component astronomical system, 3ATS. During observations, it did not demonstrate signs of active, controlled maneuvers. Its trajectory followed a smooth hyperbolic arc, fully consistent with pre-calculated gravitational models. No significant disturbances were detected that could indicate active movements or forces beyond the expected effects of solar radiation pressure or gas emissions. If this object has any capabilities for movement or active maneuvers, they are either completely inactive or so minimal that they cannot be detected under current observational conditions. This natural behavior aligns well with our understanding of interstellar objects, such as the triad including Borisov and 3C. These objects are essentially the result of planetary system formation, and their appearance can confidently be explained by theoretical models. Computer simulations show that during the evolution of any star system, a significant amount of rocky and icy debris is ejected, primarily during the early stages of formation. During these periods, gravitational interactions between forming planets disperse smaller bodies, sending them on interstellar trajectories. As a result, the galaxy should be filled with numerous such nomads, planets that began forming around other stars but were ejected into the cosmic void before they could become fully developed worlds. From the perspective of modern theories, the constant influx of interstellar visitors we are beginning to detect is a quite expected consequence of their formation process. Objects like Oumuamua, Borisov, and the triple system 3C represent the forefront of a much larger population of interstellar bodies that will, in the future, be identified and studied through new, more advanced research. For example, the launch of the Vera Rubin Observatory, planned for the end of this decade, promises to increase the detection rate of interstellar objects to several per year. This will make them more familiar and routine for astronomers, transforming them from rare curiosities into common objects of study. This statistical approach emphasizes that among the many naturally occurring interstellar bodies, there could also be artificial objects created by intelligent civilizations. If the number of naturally ejected planetoids significantly exceeds the number of artificial probes that could have been sent or left in space, then signatures of alien technology might be masked precisely within the background of natural wanderers. Detecting alien technology will require careful analysis and the identification of several artificial objects among thousands or even millions of natural ones, which is akin to searching for a needle in a haystack, an extremely challenging and labor-intensive task. An additional layer of understanding is provided by the chemical composition of the detected interstellar bodies, such as the object designated as 3ITL. Its richness in carbon dioxide broadens the spectrum of known volatile compounds found in such objects. This diverse chemical makeup indicates that, as the volume of data we collect increases and our sample of interstellar objects expands, more evidence emerges that the chemical signatures which previously seemed unusual or even artificial are actually manifestations of natural processes characteristic of planetary system formation throughout our galaxy. This fact prompts us to reevaluate our assumptions and conclusions because sampling bias, the effect arising from the fact that we predominantly detect objects that are easiest to observe, complicates our perception of the nature of discovered interstellar bodies. Primarily, our Earth-based telescopes and space surveys tend to focus on objects approaching us from specific directions, exhibiting characteristic brightness features, and moving along orbits consistent with particular geometries. As a result, the objects within our field of view, and those we confirm as interstellar visitors, may not fully represent the entire diversity of their population. For example, the first discovered exoplanets were mostly hot Jupiters located very close to their stars, and did not encompass the full range of possible planetary system types. Similarly, the 3 known interstellar objects that passed through our solar system surprised some astronomers with their approach from the southern part of the sky, contradicting initial expectations that such bodies should predominantly originate from the direction aligned with the galaxy's rotation. This unexpected trajectory suggests either that our models of interstellar object distribution are still far from perfect or that individual bodies may gravitationally interact and alter their paths, concealing their original trajectories from our view. In the future, as new astronomical tools and capabilities become available, our ability to unravel these mysteries will significantly improve. The Space and Time Survey, known as the Legacy Survey of Space and Time, conducted by the Rubin Observatory, is expected to detect hundreds of interstellar bodies during its upcoming decade-long mission, enabling us to compile statistical samples sufficient to test theoretical models of their origins, compositions, and trajectories. Space-based infrared telescopes will be able to determine their thermal properties and chemical compositions with unprecedented precision, opening new horizons in understanding the nature of these objects. As a result of such large-scale studies and expanding datasets, we will either confirm that interstellar bodies follow the natural distributions predicted by existing theories of planetary formation or discover anomalies requiring more complex and unusual explanations. If among these moving objects there are artificial probes created by intelligent civilizations, larger samples and advanced instruments will ultimately allow us to identify their artificial nature by observing subtle but persistent deviations from expected natural behavior models. One should not underestimate the philosophical implications associated with the ongoing silence of space. Every time we study a new natural interstellar object, we gain another piece of evidence supporting the hypothesis that intelligent life capable of interstellar engineering either does not exist at all, remains inaccessible to us with our current methods, or prefers not to reveal its activities, hiding behind easily recognizable signatures. The number of confirmed cases of natural interstellar visitors increases with each new discovery, strengthening the idea that cosmic loneliness might be more common than previously thought. Nevertheless, it is important to remember that the absence of evidence is not evidence of absence. Especially given the limited detection capabilities and the small volume of data collected, we cannot rule out the possibility of other forms of intelligent civilizations or technologies that remain beyond our reach for now. The universe, as is well known, holds many mysteries and surprises that often challenge our existing notions of the nature of intelligence, technology, and their manifestations in space. Each new object, whether of natural origin or artificially created by humans, becomes another argument in humanity's endless effort to understand its place in this boundless cosmic expanse. As we expand the frontiers of our research and explore increasingly hypothetical scenarios, a sharper contrast emerges between what we observe and what we can imagine. The reality of space, revealed through patient observation, meticulous analysis, and accumulated data, has proven to be so extraordinary and astonishing that it often does not require additional hypotheses or fantastical explanations. At the same time, the question remains open regarding the possible existence of other forms of intelligence in this strange reality. Future discoveries will undoubtedly provide answers to this question, and only evidence can offer the final clarity that neither theory nor hypotheses can provide. Moving on to the next section. This part will discuss the so-called cinematic nightmare, a hypothetical scenario of a silent invasion via so-called microseeds. We delve into the realm of pure scientific speculation, where the boundaries between plausible science fiction and observable reality blur, transforming into scenarios capable of challenging everything we have come to consider possible in the fields of life, intelligence, and space. What follows is the ultimate frontier of our fantasies and assumptions, ideas so speculative that they require a moment of pause and revision of many well-established scientific principles at their inception. However, all of this must remain sufficiently connected to current physical laws to fuel our imagination without exceeding the realm of possibility. Let us imagine such a scenario. 3 identical atlases are not merely ordinary space probes or even standard interstellar ships, but rather highly complex delivery systems for a more cunning and multi-stage substance or object. Inside their icy shells are microscopic devices, or perhaps biologically engineered entities created by humans, that can be conditionally called microseeds. These microseeds are in a state of hibernation, awaiting specific environmental triggers that activate their function. Among these triggers could be nanotechnological structures specifically designed to survive the harsh conditions of interstellar space for billions of years. Alternatively, they might represent some form of pan-galactic life that propagates between star systems precisely through such mechanisms. This idea is not entirely new in the realm of scientific speculation. The hypothesis of panspermia, although controversial and far from confirmed, suggests that life itself can spread throughout the galaxy via comets, asteroids, and other interstellar celestial bodies. Some scientists believe that microorganisms with high survivability could endure radiation, vacuum, and extreme temperatures of space for millions or even billions of years, successfully colonizing new worlds when encountering suitable conditions. Our hypothetical scenario goes far beyond passive panspermia. It posits that these microseeds are not merely accidental or natural forms of life, but deliberately engineered systems. They are intended not only to survive interstellar transport but also to remain in a long-lasting state of hibernation until conditions are right for activation. Perhaps these systems were created with the goal of spreading life or some other form of intelligence across the galaxy, utilizing mechanisms that are yet to be understood. Thus, the idea of such microseeds becomes one of the most fantastical yet logically plausible concepts, considering the hypothetical development of technology and biology, that could fundamentally alter our understanding of life's distribution in the universe. It is possible that these mysterious microdevices respond to electromagnetic signatures emitted by technological civilizations and activate only upon detecting certain signs of intelligent life. For example, they might react to radio transmissions, industrial pollutants, or other technological emissions indicating the presence of an advanced civilization. Or perhaps their activation is linked to solar radiation, awakening when their host object, on which they are located, approaches stars of a particular spectral type, emphasizing its stellar nature. Creating such devices would be an undertaking beyond our current technological capabilities and would pose an extraordinarily complex engineering challenge. They would need to maintain their structural integrity over billions of years, enduring cosmic radiation, exposure to interstellar dust, and extreme temperature fluctuations in the vastness of space. This would require energy sources capable of remaining operational far longer than most stars burn, and maintaining efficiency across geological epochs without degrading over time. Additionally, these microdevices would have to possess the ability to autonomously produce complex technological systems from raw materials that could be found on alien planets or asteroids, implying the presence of advanced material processing methods. If such technology were feasible, its strategic implications would be terrifying. An interstellar object, similar to what we tentatively call ice, could carry billions or even trillions of these microscopic embryos, each capable of anchoring and developing on any planet it reaches, even if that planet is distant and unfamiliar. This invasion, if one might call it that, would be silent, patient, and virtually undetectable until activated. The scenario of awakening these microscopic messengers could unfold centuries or even millennia after the 3 Atlas spacecraft pass through our solar system, remaining hidden and elusive. Their activation might be linked to certain technological thresholds that humanity would reach, such as mastering interstellar travel, achieving specific population levels, or industrial activities producing atmospheric signatures indicative of advanced technological development. Such a delay could serve several strategic purposes. First, it would provide time for detailed reconnaissance of human civilization to assess how developed and prepared we are for contact with potential extraterrestrial visitors. Second, it would ensure that activation occurs at a moment when humanity is sufficiently advanced to serve any purpose these embryos might pursue. Finally, this delay would help maintain a plausible illusion of no connection between the initial delivery and the final activation, making it impossible to easily detect any link between them. However, the question arises: how could these ideas be realized in reality, since this is where we confront the harsh and unpredictable truth? The conditions that the 3 Atlas spacecraft would face during their interstellar journey would be virtually insurmountable for any form of complex biology or technology. Cosmic radiation, slowly degrading molecular structures over millions of years, would create insurmountable difficulties in preserving the integrity of such devices or organisms. Even the most radiation-resistant organisms known on Earth would not be able to withstand billion-mile journeys through such an aggressive environment. Moreover, the chaos of cosmic gas emissions generated as they pass through interstellar dust would transform 3 Atlases into a bright, comet-like luminous body, creating additional dangers for any potential microscopic travelers, if such beings existed. Thus, despite all our assumptions and as the sublimation of surface ices on comets and asteroids gradually occurs, turning into vapor and expanding in the vacuum of space, they form the thinnest clouds. During this evaporation process, under the influence of the vacuum, ice particles, as well as tiny components embedded within the core, such as dust and other microscopic materials, are drawn into the flow. However, it is important to understand that the very nature of this process, taking place as celestial objects approach a star during their multi-billion-mile journeys, is highly destructive to any fragile structure. High temperatures, sudden pressure changes, and intense radiation cause any microscopic components embedded in the core to likely disperse or break apart over vast distances, scattering throughout space. As a result, the concentration of these particles in the vacuum becomes extremely low, significantly reducing the likelihood of their practical delivery to other systems. Even if we assume that billions of such microseeds or microscopic particles were ejected into space, the vast majority would probably be lost during the ejection phase, as they would not withstand the powerful destructive forces accompanying this process. Imagine that some of these microscopic elements somehow survived and reached the vicinity of Earth. They would face yet another barrier: dilution and dispersal in the planet's atmosphere and biosphere. Consequently, the accumulation of significant concentrations of such materials at specific points on the Earth's surface would become practically impossible. The closest estimated approach distance, about 18 astronomical units, serves as another indicator of the improbability of such a scenario. After all, a hypothetical space object similar to the Atlas would pass by Earth roughly twice as far as Mars, with no possibility of direct material exchange. For microseeds or microscopic particles to reach our planet, they would have to traverse not only the billion-mile interstellar space but also withstand intense radiation, extreme temperatures, and mechanical stresses associated with ejection and movement through space. These particles should have survived in conditions where their risk of destruction increases exponentially, starting from the moment they break off from the parent object and ending with a long journey between stars, followed by interplanetary space stretching across hundreds of millions of kilometers. Special protocols have been developed by leading space agencies to protect planets from potential interstellar contamination. These protocols involve strict precautions aimed at preventing potentially hazardous materials from reaching Earth or other planetary surfaces. Such measures include analyzing samples in specially equipped laboratories that meet high biosafety standards and thoroughly investigating any signs of biological or technological components. However, these protocols are designed for situations involving the direct return of samples brought from space, not for passive capture of microscopic particles that could have been ejected over vast distances and dispersed throughout space. The challenge of detecting and monitoring such hypothetical threats is one of the most complex tasks. How can we search for microscopic devices or organisms that could have remained in a state of hibernation for centuries without showing signs of activity? What signatures could distinguish them from millions of natural microorganisms, cosmic dust, or terrestrial contaminants? Searching for such objects essentially resembles trying to find a needle in a haystack that occupies our entire solar system. Radar observation systems with long baselines, used for tracking space debris or potentially dangerous asteroids, are unlikely to detect objects the size of microscopic seeds. These systems work well for detecting objects at kilometer scales, whereas particles measured in micrometers are far below their detection threshold. This leads us to one of the key weaknesses of our speculative scenario related to the idea of a silent, unnoticed invasion. Such a scenario violates fundamental principles of rational and logical design, since any civilization capable of creating interstellar delivery systems with a mass of billions of tons would likely have the means to employ more direct, reliable, and efficient methods to achieve their goals than tactics involving covert dispersal of microscopic seeds. Even if we assume that dispersal of such seeds is possible, they face enormous difficulties, uncertainties, and time delays associated with the need to send, spread, and establish themselves on foreign territory, making this method practically ineffective. In comparison, there are other, more straightforward ways of interaction or influence: directed energy transfer, the use of spacecraft specifically designed for reconnaissance or impact purposes, or even simple radio communication. All these alternatives offer faster, more predictable, and less risky ways to achieve our goals than dispersing microscopic seeds into space. However, it is precisely this scenario, a silent invasion, that serves as an important tool in our exploration, as it demonstrates how our imagination often outpaces actual physical capabilities. Reflecting on the cosmic mysteries we face, it becomes clear that the sense of wonder, as well as the slight anxiety caused by these enigmas, drives scientific discoveries. At the same time, this very feeling can give rise to fears that go beyond reasonable assumptions, turning scientific curiosity into a kind of troubling fantasy. Therefore, it is crucial to distinguish between prudent caution and unfounded speculation, especially when dealing with phenomena that evoke unprecedented interest and complexity. In our work of documenting such scenarios, it is essential to emphasize their speculative nature so that viewers or readers understand we are exploring realms of imagination, not strict scientific facts. These mental experiments and hypotheses can be very useful for broadening our horizons and understanding possible scenarios. However, they should not be perceived as likely or even plausible realities. Nevertheless, there is an opposing viewpoint, which is the simplest and most convincing. According to it, the behavior of an object known as the three-lobed signal or 3L can be fully explained by natural causes. The most obvious and logical explanation is that it is merely cometary dust behaving exactly like any other cometary material. This object exhibits all the characteristics expected from natural cometary matter: corresponding spectroscopic signatures, predictable behavior when heated by sunlight, and models of gas emission that align precisely with solar heating. No additional hypotheses or assumptions are necessary to explain its observed properties. All we need to do is recognize that this object is a typical representative of cometary dust, and its behavior can be explained scientifically based on known physical processes. As our research progresses and we approach the conclusion of this speculative journey, increasingly dramatic scenarios and hypotheses emerge. However, it is worth pausing and reflecting on what these mental experiments teach us about human psychology and our nature. as well as how we interact with cosmic uncertainty. Our tendency to seek exotic explanations for unusual phenomena reflects not only our creative potential but also an inner anxiety related to our place in the universe. This boundless and often indifferent cosmic environment evokes both admiration and fear within us. And yet, despite all its mystery and inexplicability, the tangible and measurable object known as the three-lobed signal or 3ATS represents something quite astonishing and worthy of attention. This enigmatic object, moving at a speed that exceeds all our expectations, itself serves as an important goal in our ongoing and continuous effort to understand humanity's place within the vast context of the universe. Each such initiative, each hypothesis, and each theoretical analysis bring us closer to unraveling the true nature of the surrounding world, even though the boundaries of our understanding are often quite blurred and fluid. In this pursuit, we strive to expand the horizons of knowledge to the maximum, while also recognizing the limitations imposed by the nature of physics itself and the existence of evidence supporting various hypotheses. It is precisely through the natural processes operating within the universe that it manifests so astonishingly and strangely that it sometimes seems to transcend all our notions. Perhaps many of its aspects appear so incredible and incomprehensible to us that even the most vivid imagination cannot fully grasp them. However, despite its apparent alienness and complexity, these mysteries are revealed step by step, through patient observation, careful analysis, and a systematic approach. Ultimately, it is these methods that allow us to penetrate the deep secrets of the cosmos, understand its true nature, and establish the boundaries of possible explanations. Part 11. Imagine what would happen if the 3ATS turned out to be an alien visitor in our system. How would we react to such an unexpected encounter? The answer to this question remains a testament to the best aspects of human scientific cooperation. This collaborative process can be likened to choreography, where numerous telescopes, scientific institutes, and individual researchers work in synchronized motion, like participants in a complex and harmonious dance, to maximize the potential of this unique opportunity. Within a few hours after the initial detection of this mysterious object, which occurred thanks to the work of the Atlas Observatory on July 21, the entire global network of telescopes and astronomical stations began operating in coordinated modes. This served as a vivid confirmation of how truly international modern astronomy is, a collective effort uniting scientists from around the world. The response was immediate, based on protocols developed over many years, more than a decade of active work in discovering and tracking asteroids and comets. At the heart of this activity was the Center for Small Planets at the Astrophysical Observatory affiliated with the Smithsonian Institution, located at Harvard University. This center has become the central hub for astrometric observations, collecting and processing information about the object's position using data obtained from all corners of the globe. Each new dataset refined its orbital parameters, bringing scientists closer to understanding the true scale and characteristics of this mysterious visitor. At the same time, the European Space Agency, through its Space Situational Awareness Program, added its capabilities for tracking, while the Planetary Defense Division of the National Aeronautics and Space Administration, NASA, carefully assessed any potential risks. However, the collision probability calculation was conducted very quickly and showed that there is no collision threat in this case. But, most importantly, the nature of this object, as an interstellar traveler, sparked not only scientific interest but also increased vigilance, since such phenomena require special attention and deeper analysis. To study this visitor, the Hubble Space Telescope was engaged, with a priority observation assigned to it, interrupting previously scheduled programs to capture this unique event. Following it, the James Webb Space Telescope also focused its efforts on spectroscopic analysis of the unusual comet, which was dominated by molecules of carbon dioxide. This research significantly expanded our knowledge of the chemical composition of cosmic objects and their origins. Ground-based observatories located around the world, from the Atacama Desert in Chile to Mauna Kea in Hawaii, contribute to this effort. Information surrounding the three well-known astronomical laboratories, often referred to as the 3ASLs, has remained entirely transparent and accessible to the public to this day. Official sources, such as the NASA website, regularly publish updates regarding observation results, new data, and technical specifications. These pages offer not only dry figures and diagrams but also explanations intended for the broadest audience, enabling even those without specialized knowledge in astronomy to understand what is happening. The European Space Agency also participates actively. It publishes similar reports and news, emphasizing the collaborative and cooperative nature of all observations and research. This approach helps create a sense of openness and trust, strengthening international cooperation in space exploration. In addition to official organizations, popular astronomical publications like Sky and Telescope provide not only technical details but also practical advice for amateurs and professionals eager to observe this interstellar guest on their own. For those equipped with telescopes and enthusiasm, such publications serve as valuable guides and help prepare for potential observations. All of this creates an image of a transparent system in which information is freely and openly disseminated, strengthening trust and interest in space research. However, imagine a hypothetical situation where our initial assumptions and speculations, arising during the early stages of this investigation, prove to be correct, and future observations begin to reveal signs that cannot be explained by conventional natural processes or known technologies. The situation could then change dramatically. For example, radio transmissions that appear coordinated and controllable, or the detection of objects whose trajectories cannot be explained by current models, would become evidence of unknown forms of activity. In such a case, how would our institutions, scientific and administrative structures, scale their efforts to handle a discovery that could surpass all previous breakthroughs in human history? Existing protocols and procedures provide some guidelines. The International Astronomical Union, a reputable organization in this field, has already developed a series of protocols for verifying unusual and anomalous claims. These protocols involve engaging multiple independent observatories to confirm or refute the data and to avoid errors or false alarms. If unusual signals or objects are confirmed, additional verification and coordination are required to ensure that the results are scientifically sound and reliable. The Institute of Network Technologies and Communications has established special communication protocols designed for first contact scenarios. These guidelines include procedures for information exchange between countries, measures for public notification, and coordination of international response efforts. A key task in such a situation is not only collecting and verifying data but also ensuring coordinated actions to prevent panic and chaos. Space agencies worldwide have also developed planetary protection procedures aimed at preventing possible contamination of Earth or the spread of potentially hazardous extraterrestrial life forms. These measures include strict monitoring of asteroid and space objects, as well as protocols to prevent unwanted contact with alien organisms. However, it should be noted that all these systems and structures were primarily created to prevent accidental and harmless incidents, not to handle situations involving the detection of active extraterrestrial technologies operating within our solar system. The scale and complexity of such coordination could be unprecedented for modern science and international politics. In the event of an actual discovery, the situation would require swift and organized response. First and foremost, the question of jurisdiction would arise. Which international organization has the authority to manage a situation related to the first contact? How can coordination be arranged among states that might perceive the discovery as either a threat or an opportunity for technological breakthrough? What should be done if scientific curiosity and the pursuit of knowledge drive us? The detection of confirmed extraterrestrial life or technology on our planet would inevitably become one of humanity's most challenging tests, as it would necessitate an assessment of all aspects of our capabilities in space exploration and defense. Currently, our modern spacecraft heading toward the outer boundaries of the solar system require several years to reach their destinations, and achieving interstellar speeds would take decades. In such a scenario, if the discovered object truly turns out to be of artificial origin and communication needs to be established, the only practically feasible option would be to use radio signals. However, this is only possible if extraterrestrial technology employs communication protocols that we can recognize or decode. The absence of more advanced and modern interception or interaction methods underscores the current limitations of human technology in space communications and defense. Despite decades of impressive achievements in robotics, reconnaissance, and automated systems, we remain confined to our nearest cosmic surroundings, where transit times for objects are measured in years, not months. This means that any significant interaction with rapidly moving interstellar objects, such as potential spacecraft or other forms of extraterrestrial technology, would require technologies that we do not currently possess and are unlikely to develop in the short term to be relevant for such objects. As a result, the strategy for information exchange and public communication will face unprecedented challenges. How should we properly announce the evidence of extraterrestrial intelligence without triggering panic and social upheaval? It will be crucial to adopt a very cautious and measured tone, similar to how space agencies have previously informed the public about discovered objects, such as the triclase, emphasizing the scientific importance of the discovery while minimizing sensational interpretations. However, situations involving more significant and potentially dangerous discoveries will demand the development of new communication approaches to maintain public trust and the authority of research institutions. Learning from past false alarms and misunderstandings will be a decisive factor in preparing for such scenarios. For example, the signal detected by researchers in the network in the 70s of the last century, known as the "wow" signal, caused enormous excitement and speculation about extraterrestrial sources. However, it ultimately turned out to be a one-time event that could neither be confirmed nor repeated. More recently, the unusual properties of the object named Oumuamua led to brief speculation about its possible artificial origin. Nevertheless, more conventional explanations related to natural phenomena were soon proposed. This experience taught scientists and science communication specialists the importance of balancing curiosity with caution, to avoid making hasty conclusions and unnecessary panic. Media management will become the cornerstone of any response to confirmed extraterrestrial technologies or entities. In an environment of constant 24-hour news flow, saturated with dramatic headlines, it is very easy to replace careful scientific analysis with speculation and disinformation. Social platforms will face a serious challenge: how to distinguish trustworthy sources of information from fake news, conspiracy theories, and forgeries that can spread at an incredible speed. Equally important will be the question of the economic consequences, which could be significant and require thoughtful and well-planned responses. Global and local response systems must be prepared for rapid and coordinated action to minimize potential harm and maintain stability. Ultimately, a successful and balanced response to such a discovery is not only a technological challenge but also a matter of social trust, informational culture, and responsibility toward all humanity. Financial markets will undoubtedly experience significant fluctuations and sharp volatility in the near future, as investors and analysts attempt to comprehend and account for all possible consequences related to the confirmed fact of extraterrestrial technology. Primarily, this event could fundamentally alter the existing order, as entire industries that previously appeared stable and predictable may face fundamental questions about their future. If extraterrestrial science provides revolutionary alternatives to current solutions in energy, transportation, or manufacturing, many companies and entire sectors could be on the verge of transformation or even disappearance. In this context, the stability of the global economy will depend not only on technological progress but also on how effectively and promptly institutions can manage this transitional period, from familiar speculative models to new realities confirmed by scientific facts. Educational institutions, in turn, will face immediate and serious pressure to revise their curricula, pedagogical approaches, and research priorities. They will need to rethink their fundamental assumptions about humanity's place in the universe and incorporate new knowledge and ideas into their educational plans, concepts that were previously considered science fiction or hypothetical notions. As a result of this process, significant changes will occur across scientific disciplines: astronomy, physics, biology, anthropology, theology, and political science, all of which will undergo transformations in understanding how reality is structured and the role humans play within it. Universities, which for centuries have built and developed accumulated expertise in studying terrestrial phenomena and processes, will have to quickly adapt their programs, integrating concepts of non-human intelligence and new forms of cognition. This demands a fundamentally new approach to education and research activities. The time constraints associated with the high-speed trajectory of interstellar travel give particular urgency to any hypothetical response scenarios. Unlike the gradual approach of astronomical phenomena or cosmic objects, the sudden appearance of interstellar visitors and their rapid disappearance are governed by the laws of physics and the unpredictability of human capabilities. Any serious response must be developed and implemented within a very short time frame, within months, not years, compressing and complicating typical decision-making processes and threatening the effectiveness and adequacy of institutions. Nevertheless, the experience gained through the Object 3 and Atlas project demonstrated remarkable efficiency even under such constraints. The global astronomical community was able to identify this extraterrestrial object, confirm its interstellar origin, coordinate and conduct multi-wavelength observations, and begin detailed data analysis within just a few weeks of its discovery. This example clearly shows that existing institutions and procedures, despite their imperfections, possess a powerful potential to solve even the most unprecedented and complex problems. The development of theoretical frameworks for response and preparedness for confirmed contact with extraterrestrial civilizations has taken decades and was based on the work of research networks, astrobiologists, scientists from various countries, and international organizations. Although these preparatory efforts could not foresee all possible scenarios, they served as an important starting point for rapid and effective decision-making in emergency situations. The most important and valuable outcome highlighted within the TRI and Atlas project was that humanity's response to the discovery of an extraterrestrial object was more driven by curiosity than fear, focused on scientific investigation rather than speculation, and emphasized international cooperation rather than competition and secrecy. These values, transparency, shared observation exchange, and collective scientific efforts, represent the most prudent and progressive approach humanity can take in exploring cosmic mysteries. They lay the foundation for a responsible and collaborative pursuit of understanding the universe. The question remains whether current technological capabilities can facilitate genuine first contact with extraterrestrial civilizations and whether such contact can be achieved in a coordinated, organized manner. A well-founded professional analysis based on three main areas of technical and scientific development offers some hope that humankind is capable of handling even more complex and unusual cosmic encounters. Gradually, we are shifting from simple, sometimes speculative thoughts about potential contact with aliens to a more balanced and scientifically grounded discussion of space exploration prospects. This approach involves utilizing modern scientific methods and systemic analysis. The response obtained within the framework of the third direction serves as a good example of how modern civilization approaches working with the unknown. In this case, technological capabilities are combined with institutional coordination and genuine intellectual curiosity, characteristic features of research conducted within the Tri-Atlas project. This project, in turn, exemplifies how we engage with the universe's mysteries, which may prove even more significant for our understanding of our place within the cosmos. Let us also consider the issue raised in Part 12, the dilemma of restraint versus curiosity. This very dilemma underpins many aspects of human exploration and progress. As always, humanity faces the challenge of balancing the pursuit of new knowledge with the potential risks that may arise during this quest. Such contradictions have historically motivated us to explore oceans, climb mountain peaks, and send missions into space, despite the dangers involved. In the case of the object known as Trialos, this balance predominantly leans toward curiosity, and there are compelling reasons for this. Its trajectory and physical properties exclude most scenarios involving potential containment, while simultaneously expanding the horizons for scientific discovery. The modern planetary protection doctrine, built upon years of experience in space exploration, serves to assess risks and develop precautionary measures. These approaches are intended not only to protect Earth from potential contamination by extraterrestrial microorganisms but also to prevent possible impacts of terrestrial life on other planets and moons. In particular, strict sterilization protocols are applied to spacecraft during missions involving sample return from Mars or other investigations related to potentially habitable worlds, to avoid reverse contamination. For example, in the case of the Perseverance rover, which collects samples from the surface of Mars, preliminary plans included extraordinary precautions to ensure their safe return. This approach was developed to guarantee that any hypothetical microorganisms remaining on the samples would not reach Earth's biosphere and cause undesirable consequences. Similar attention is given to other missions, especially those sent to moons where habitable environments might exist, such as Europa or other similar objects. These spacecraft undergo rigorous sterilization procedures and other safety measures. However, the scenario involving the object Trialos significantly differs from traditional planetary protection protocols. Its closest approach to Earth is about 1/8 of an astronomical unit, and its projected trajectory lies approximately 270 million kilometers away, ruling out any possibility of direct material exchange or contact. In this case, interception or capture of the object by a spacecraft is not planned. Moreover, current technology does not even theoretically allow such operations. Considering current scientific and technological achievements, as well as the extreme speed at which Trialos moves, the question of restraining this celestial body becomes practically meaningless. It will never come close enough to be contained or stopped. In this sense, the issue of containment shifts to a purely theoretical or academic level, as there are no real capabilities to prevent its approach. Thanks to the fact that astronomical data and research results were organized at a sufficiently safe and reliable distance, the scientific community was able to establish an entirely open and transparent approach to information exchange. This approach made available for analysis images obtained from the Hubble Space Telescope, as well as spectroscopic data collected by the James Webb Telescope, along with numerous ground-based observations. All these materials were stored in standard astronomical archives, creating a foundation for global scientific collaboration. Now, researchers, regardless of their geographical location, could access the same datasets, analyze them, compare conclusions, and verify each other's results. Such transparency and openness represent the best example of the scientific method in its ideal form, where knowledge is freely shared and results undergo multiple verifications by different scientists. This allows several independent research groups to study the same evidence and reach consistent conclusions regarding the origin of the discovered object. At the core of this approach is the culture of open archives, which has developed around the largest space telescopes and deserves special recognition for its importance and effectiveness. For example, the Mikulski Archive for Space Telescopes provides free access to images and spectra obtained from the Hubble and Webb telescopes to any scientist with internet access. This democratizes astronomy, making research opportunities accessible to specialists worldwide, something that was impossible just a few decades ago when resources and data remained confined to a small circle of experts. Similar archives are created and maintained by the European Southern Observatory for ground-based observations, expanding research capabilities and providing access to data for a broad range of scientists. Meanwhile, within citizen science, amateur astronomers continue to contribute by sharing their images and light curves through various platforms and projects. This open and accessible scientific environment sharply contrasts with the secrecy often present in military or intelligence structures, especially in cases related to potential contact with extraterrestrial civilizations. The preference for transparency by the scientific community is driven not only by practical considerations related to the need for information exchange but also by deep philosophical beliefs that knowledge about the nature of the universe should be accessible to all. This approach reflects the conviction in the universality of scientific truths and the necessity of their collective discussion and verification. The 3 Atlas study vividly demonstrates how these principles work in practice, even when studying phenomena that could essentially become our first contact with potential extraterrestrial intelligence. An overview of the informational space around 3 ATLAS shows how, in the context of global and instantaneous communication, both advantages and challenges are simultaneously realized. On one hand, legitimate scientific results are quickly disseminated through professional networks and platforms, enabling scientists worldwide to interact and collaborate in real time, even while on different continents. This creates conditions for nearly simultaneous research and exchange of ideas, significantly accelerating progress. On the other hand, the same channels of communication that facilitate productive scientific exchange can also serve as tools for spreading misinformation, speculation, and sensational distortions. They are creating a platform for the dissemination of false theories and unfounded hypotheses, which makes it difficult for society to objectively perceive scientific facts. In recent years, the models of spreading disinformation around astronomical discoveries have become increasingly complex and sophisticated. Social media algorithms, which prioritize engagement and popularity over accuracy, amplify the tendency to spread sensational claims, conspiracy theories, and baseless assumptions, often at the expense of scientific rigor and verified information. In such a situation, the ability to distinguish legitimate scientific uncertainties, those that stimulate further research and the pursuit of new knowledge, from dangerous misinformation becomes particularly important. In the world of scientific research and information exchange, sources that do not hold leading positions in terms of status and authority are often encountered. It is these sources that sometimes exaggerate preliminary results that have not yet undergone comprehensive verification and confirmation. They tend to mix scientific facts with conjectures and assumptions, creating confusion and misleading the public. In some cases, these sources spread conspiracy theories, claiming that governments are hiding information about contact with extraterrestrial civilizations or unknown technologies supposedly stored in secret archives. In this dynamic flow of information, visual communication plays a crucial role, as images and graphic materials can enhance the impact and attract attention. For example, images obtained by the Hubble and James Webb telescopes, processed and enhanced to reveal scientific details more clearly, often look very impressive and even otherworldly to the general audience. However, behind their dramatic and mystical appearance, there is often a scientific explanation that does not involve extraterrestrial technologies or supernatural forces. The main task of specialists when publishing such images is to present them in a context that emphasizes their true scientific significance rather than sensationalism. It is important to show that the observed features and anomalies confirm known physical mechanisms, such as cometary behavior, rather than serving as evidence of extraterrestrial technologies or contacts. At the same time, questions arise about the boundaries of information withholding and the necessity of transparency. Discussions about scientific discoveries frequently include the idea of whether certain achievements should remain secret or be shared with restrictions. In the case of astronomical discoveries, most scientists and researchers agree that restrictions on data dissemination are unjustified. The scientific community has unanimously decided that the benefits of open knowledge sharing far outweigh the hypothetical risks associated with potential leaks of sensitive information. This approach is based not only on pragmatic considerations but also on deeper philosophical principles. After all, astronomy is essentially a global science that unites researchers from around the world with common goals, sharing data, verifying and re-verifying results, building upon collective knowledge. Such an international and open approach fosters accelerated progress and increases trust in scientific conclusions. Philosophically, views from space have always served to unite humanity rather than divide it. The idea that we are all inhabitants of one planet and that space is a shared heritage helps to soften national and political disagreements. Historical experience shows that open and transparent astronomical discoveries, even if they seem anomalous, have not led to catastrophic consequences. For example, in the 1960s, the discovery of pulsars was made, which were tentatively labeled as LGM, Little Green Men, but ultimately, these discoveries helped reveal new physics rather than confirm hypotheses about extraterrestrial intelligence. Similarly, the signal detected by network researchers and dubbed WOW remained unexplained, but was carefully documented and published for the public, demonstrating transparency in the process. Even the unusual properties of Oumuamua, which sparked much debate and speculation, were studied within the framework of international cooperation, without secret or closed programs. This approach confirms that scientific curiosity and the desire to understand are the most important driving forces. Curiosity above all else often motivates amateur astronomers with modest equipment to produce their own images and light curves, supplementing professional observations. These data, collected by citizens of the world, ultimately form a valuable part of the knowledge base that contributes to expanding our scientific understanding. In an environment where political restrictions could hinder such democratization of research, open access to data has become a crucial factor stimulating genuine scientific development. An analogous example is the SFC mission, which is engaged in mapping. Wide-field infrared missions, such as the SPHERICS project, can significantly complement detailed spectroscopy provided by observations through the Webb instrument. Collectively, these methods enable the creation of comprehensive and highly accurate portraits of interstellar objects, called visitors, which previously could only be inferred indirectly. No existing instrument or method allows for such a deep and multifaceted understanding of these objects as the combined use of wide-field infrared observations and spectroscopy. In the future, with technological advancements and the expansion of observatory capabilities, large-scale studies of space and time are planned, which could lead to a true revolution in our understanding of interstellar bodies. The Vera Rubin Observatory, scheduled for launch, promises to discover hundreds of similar objects during its planned operation, which will fundamentally change our understanding of the nature of interstellar visitors. This statistical approach will reveal patterns and distributions of these objects, either confirming the hypothesis that most of them are natural phenomena governed by predictable and regular distributions, or uncovering anomalies that will require more exotic and unusual explanations. The institutional approach to studying these mysterious objects has been shaped by the experience of the Tree Atlas project. This experience demonstrated that rapid coordination between different observatories, transparent and open data sharing protocols, and a focus on international collaboration create a foundation for successful scientific investigations involving even more unusual and rare discoveries. In the future, if truly anomalous interstellar objects are discovered, the scientific community, equipped with extensive experience and well prepared for such challenges, will be able to study them effectively, using the same collaborative methods and open approaches that proved successful in the Tree Atlas project. This experience shows that maintaining a balance between skepticism and openness, characteristic of professional astronomers analyzing data, is a crucial model for future discoveries. Healthy scientific skepticism requires rigorous and convincing evidence when evaluating unusual claims and phenomena, but it should not become an obstacle to accepting new possibilities that go beyond existing theories. The Tree Atlas project demonstrated that this balance can be maintained, recognizing the unusual properties of discovered objects while avoiding unfounded speculation. Such an approach not only preserves scientific integrity but also paves the way for new ideas and hypotheses that could expand our knowledge of the cosmos. The assessment of risks associated with the potential approach of interstellar visitors will be based on the precedent set by the Tree Atlas project. If an object passes through our solar system exhibiting behavior consistent with comet physics and shows no signs of anomalies, such cases can be considered typical and safe. They establish baseline expectations for future interstellar objects. However, objects that significantly deviate from this model, for example, exhibiting unusual properties or behaving differently, will require the development of new approaches and methods of study. In such cases, the assumption will likely remain that natural explanations must be thoroughly tested before considering more exotic hypotheses. The educational value of the Tree Atlas project extends beyond its immediate scientific results. This project vividly demonstrates how modern astronomy operates as a systematic enterprise based on collaboration and transparency. It shows how institutions around the world coordinate their efforts in response to new discoveries, how data sharing facilitates rapid progress and the advancement of knowledge. Moreover, it illustrates that professional skepticism grounded in evidence helps prevent premature conclusions and unfounded assumptions, especially when dealing with unusual phenomena that require deeper analysis. This approach enables us to move forward with confidence, expanding the boundaries of human understanding of the universe, focusing on curiosity rather than fear, on cooperation rather than competition, and on evidence rather than speculation. All of this fosters hope and optimism about our ability to uncover new horizons in space exploration. Such an attitude reassures us that in the coming years and decades, even more profound and exciting cosmic discoveries await, capable of transforming our understanding of the universe and our place within it. Part 13. The Scales of the Cosmos and Our Signals. The journey that brought the so-called three aces to our interstellar doors spans such vast distances and time scales that it inspires awe while also posing significant challenges for the human mind. Yet, understanding these scales is key to grasping both the significance of the discovered object and our own position in this boundless galactic era. When we speak of the origin of these signals or objects from the so-called thick disk of our galaxy, we refer to a history that began when the age of the universe was less than half of what it is today. During those epochs, stellar populations differed markedly from what we observe now, and the Milky Way itself was in an early and highly chaotic stage of formation. The thick disk consists of an older generation of stars formed during the galaxy's early turbulent periods approximately 10 to 12 billion years ago. Unlike the thin disk, where our Sun resides and where stars move along relatively circular orbits around the galactic center, the thick disk contains stars with more eccentric, inclined, and often highly elongated orbits, reflecting the harsh conditions and dynamic environment of their formation epoch. If indeed these are three aces originating from this ancient layer, then their cores contain records of the stellar neighborhoods that existed long before our solar system appeared. Within the core of these objects lies the history of star systems that existed even before molecular clouds in which stars first began to form. The scale of this journey seems almost poetic when visualized. The three Alas could have wandered through the galaxy for billions of years, during which entire generations of stars have come and gone. The massive stars that existed at the time of their presumed journey's beginning have long since exploded as supernovae, enriching space with heavy elements and triggering new waves of star formation. Over this time, entire planetary systems may have formed, evolved, and possibly disappeared, while potential life developed countless times throughout their long interstellar voyage. Traveling through the vast and dark emptiness of space is something beyond human imagination. If we assume that the three Alas indeed roamed the galaxy for at least 5 billion years, a conservative estimate based on their origin from the thick disk, then their journey has lasted more than 1,000 times longer than the existence of complex life on Earth. During this period, our planet has experienced many significant events: the Cambrian explosion, when the first complex multicellular organisms appeared, 5 major mass extinctions, the rise and fall of dinosaurs, and finally, the emergence of human civilization. But for this cosmic wanderer, for the three Alas, the entire history of humanity is merely a tiny, microscopic fraction of their multi-billion-year journey. All we know about our world is just one of the last microseconds of this incredible cosmic voyage. The distances they have traveled are equally staggering. They are so vast and difficult to comprehend that they seem almost unreal. All of this is not just numbers or abstract quantities. It's a reality that highlights the scale and complexity of the processes occurring in space. Even at a fantastical speed of 333,000 miles per hour, significantly exceeding the capabilities of modern technology and even hypothetical spacecraft, crossing the immense expanses of our galaxy would still take millions of years. Imagine that any moving object, even one traveling at such an incredible speed, would still be forced to cover enormous distances between star systems, and each journey would be a long and arduous trek through cosmic darkness. During their voyage, they would likely encounter hundreds or even thousands of different star systems, passing close enough to feel their gravitational influence. These interactions could be so insignificant that the object might not notice them at all, remaining in its cosmic adventures as if engaged in a silent and hidden game deep within the infinite universe, where no one would be able to detect or record such encounters. Every gravitational interaction, even the slightest one, would influence the trajectory of this cosmic wanderer, subtly altering its speed and direction, much like in a complex and endless game of pinball played on the scale of the entire galaxy. These small, barely noticeable changes, accumulated over millions of such encounters, could explain the incredible velocity at which the current object, known as the triplet atlas, is moving. Each pass by a stellar body would impart a slight impulse, similar to how a gentle breeze can slightly accelerate a boat, and over time, these impulses would add up, transforming it into a truly swift traveler rushing through the galaxy at a frantic pace. The chemical composition of this object becomes particularly significant when viewed against the backdrop of the galaxy's entire history and the diversity of formation conditions in which it originated. The three atlases, containing a rich array of chemical elements and compounds, can tell us much about the environment in which this cosmic visitor was formed. Its abundant carbon dioxide content suggests that it likely originated in an environment very different from the conditions that existed in our solar system. Such an environment could have been dominated by entirely different nuclear synthesis processes, alternative architectures of planetary systems, and a unique composition of the interstellar medium where stars and planets formed. This object is a kind of unique specimen of alien chemistry, bearing molecular signatures left by the stellar neighborhoods that we may never directly observe or visit with our own eyes. Thanks to so-called chemical archaeology, we can expand our knowledge of galactic evolution by studying such objects and interpreting their chemical makeup, offering us unique opportunities that conventional astronomy cannot provide. If we are capable of studying distant stars through their light, using spectroscopy to determine their properties, then interstellar objects like this one provide us with tangible physical samples of material that formed around stars billions of years ago. It's akin to discovering pieces of alien worlds delivered directly to our doorstep, along with information about isotope ratios, mineralogical composition, and volatile inventories. All of this offers invaluable insights into the conditions under which these objects formed, information that helps us understand the history and development of entire galaxies. Our own radio signal, or, in scientific terms, the radius, an expanding sphere of electromagnetic radiation, serves as a modest testament to humanity's presence in space. Since the advent of the first wireless transmissions, created by Guglielmo Marconi at the end of the 19th century, our radio signals have been propagating outward at the speed of light. Today, they have reached approximately 120 light-years from Earth, which is undoubtedly impressive. However, to grasp the scale of this achievement, it is necessary to remember that our galaxy, the Milky Way, is a vast concept. What today's scientists and researchers find quite astonishing is the idea of systems capable of emitting quiet, barely perceptible whispers, as if invisible threads weaving through space, signals that would be detectable by any potential listeners located near the closest star systems. The notion that three atlases, or other hypothetical objects, could have been drawn into our solar system by electromagnetic forces seems fantastical, yet it remains entirely plausible. Their signatures become truly incredible when considering not only the presumed age of these bodies or objects but also the minuscule fraction of the galaxy covered by our radio presence. The magnitude of this scale becomes clear when we think about the entire galaxy and how little of it we are capable of reaching with our radio programs. The silence we experience when listening for radio signals from other civilizations is nothing but a profound silence underlying the so-called Fermi paradox. This appears less surprising when viewed on the scale of the entire galaxy. Even if we assume that the galaxy is populated by thousands of civilizations actively transmitting radio signals, the distances between them become an insurmountable barrier. These distances, measured in billions or trillions of kilometers, turn even the most powerful signals into barely perceptible faint sparks. The inverse square law governing the propagation of electromagnetic radiation states that doubling the distance from a source reduces its brightness by a factor of 4, making interstellar communication an extremely challenging task for any civilization, even one with technologies far surpassing our current capabilities. To send a signal strong enough to be easily detected across interstellar distances would require energy resources comparable to those of small stars, roughly equivalent to the energy spent on production and consumption by entire countries over a year. Even when using narrowly focused, directed beams aimed at specific systems, the energy demand remains exceedingly high. Creating signals that could be detected hundreds or thousands of light-years away is a task that demands energy generation capabilities far beyond what modern civilization can provide. These physical limitations undoubtedly explain why our efforts to detect artificial radio signals over decades have yielded no convincing results. The same energy considerations are relevant to interstellar travel, providing important insights into the feasibility of various scenarios we have considered in this study. Even to develop a small interstellar probe capable of reaching the speeds necessary for rapid transit between stars, an amount of energy equivalent to the annual consumption of major industrial nations would be required. Larger spacecraft, which are more massive and complex, will demand energy reserves that are likely to surpass the current capabilities of human civilization in energy production. In this context, it becomes clear that the potential use of gravitational interactions, so-called gravitational slingshots, to achieve extreme velocities, as proposed in some hypotheses, is a quite realistic scenario. Such a mechanism, based on the natural properties of the galaxy, allows objects to accumulate energy through numerous interactions with stars and gravitational encounters, gradually accelerating without the need for exotic technologies or artificial acceleration systems. The detection of interstellar objects on such scales becomes even more justified when considering the statistical and gravitational effects acting within the galaxy. The more extensive and diverse our experience and observations become, the clearer it will be that these objects can reach such high speeds that their behavior and properties require a new perspective on their formation and movement processes. In light of these large-scale and complex processes, discovering such bodies is not only a matter of technological implementation but also a reflection of the broader understanding of their nature. If we assume that the process of planetary system formation regularly involves the ejection of vast quantities of rocky and icy fragments, then based on current computer models, we can conclude that our galaxy must be filled with trillions of such wandering objects, similar to the one we conditionally call TRI. These interstellar wanderers are the result of numerous processes and events occurring over billions of years, and their numbers far exceed the handful of objects we manage to detect annually with current technologies. The Rubin Observatory, even with its capabilities, registers only a small fraction of this enormous population, indicating significant limitations in our observational methods and technological tools. This statistical reality implies that the chemical and physical diversity of interstellar objects we have already detected represents only a small segment of the entire spectrum of possible compositions and characteristics existing within the galactic environment. In the future, with technological advancements and expanded observational scope, we may encounter objects with even more astonishing and exotic properties than the three catalogs already discovered. This will broaden our understanding of the conditions and processes occurring around distant stars, as well as help answer questions about the origin and evolution of interstellar bodies. The timescales characteristic of galactic evolution also provide an important basis for interpreting the significance of the three atlases we have discovered. Over billions of years, the chemical composition of our galaxy has been constantly changing, driven by processes in which stars played a key role. Each new generation of stars formed from heavier elements produced in previous stellar eruptions, which were then dispersed throughout the galaxy via supernova explosions. Objects that originated in the early stages of this evolution, such as the three atlases we identified, likely reflect the chemical profile of a young, less metal-rich galaxy, assuming our age estimates are correct. This environment was radically different from what we observe today, with a lower abundance of heavy elements and different formation conditions. This temporal perspective complicates the interpretation of the chemical signatures we find in ancient interstellar bodies, as their composition bears witness to conditions that existed hundreds of millions or even billions of years ago. Notably, the dominance of carbon dioxide in the composition of the atlases makes them unusual among modern comets. While most contemporary objects in our solar system display different chemical ratios, the prevalence of carbon dioxide suggests these bodies probably formed under conditions typical of young stars or first-generation stellar systems. These conditions included unique thermal regimes and compositions distinct from solar, indicating that their origins are linked to the early epoch of galactic formation. Understanding these ancient conditions is key to deciphering the early stages of the galaxy's chemical evolution, as such objects serve as a kind of preserver of information about eras for which we have virtually no other sources. As we approach the conclusion of our study of the atlases and their significance, it becomes clear that the scope of this discovery extends far beyond ordinary astronomical observations. They remind us of the exceptional nature of this object, which bears witness to long and complex processes of galactic evolution, and simultaneously highlight how limited our current capabilities are for fully understanding these phenomena. We are not merely studying another interstellar rock, we are examining an object that has endured through billions of years, containing chemical signatures of stellar environments with which we have never interacted directly. It provides a unique physical link to events that occurred long before the formation of Earth, and despite its importance, remains comprehensible within the framework of modern scientific models. His behavior is governed by the laws of physics. The combination of such an unusual origin and familiar behavior is a vivid testament to both the diversity and the common unity of natural processes occurring throughout the galaxy. It is this cosmic scale perspective, based on the universal laws of nature, that underpins our latest reflections on what Triolus, this mysterious object, represents for human perception and our further relationship with the cosmos, which has bestowed life upon us. In this context, it is important to emphasize that Part 14 is dedicated to the theme of hope, which manifests in silence and in data obtained through scientific means. Perhaps the most valuable gift that Triolus can offer humanity is not in any exotic hypotheses about its origin or purpose, but in the simple yet crucial fact, its safe passage through our cosmic neighborhood. In an era when global challenges often seem insurmountable and the future appears hazy and uncertain, there is something very reassuring in the fact that a cosmic visitor like Triolus appears exactly at the prescribed time, behaves strictly according to the laws of nature, and unobstructed recedes into interstellar darkness, without disrupting a single earthly sunset. Such calm and confidence in safety are not trivial achievements. They symbolize the triumph of scientific understanding over cosmic fear, the victory of careful and systematic observation over unfounded assumptions and guesses. When Triolus was first discovered, rapidly approaching our solar system at an unprecedented speed, many might have felt anxiety in the face of the unknown. However, despite this, just a few weeks after the discovery, international groups of scientists and astronomers were able to precisely calculate its trajectory, carefully analyze its chemical composition, and with high confidence predict its harmless flyby past Earth. This example vividly illustrates the power of human knowledge and the capacity for collaboration in solving the most complex problems. The scientific results obtained from studying Triolus already surpass most astronomical discoveries in their entire history. Notably, its unusual chemical composition, rich in carbon dioxide, challenged established notions of typical comet chemistry. This compelled scientists to develop new models explaining how the ratios of volatile substances can vary significantly among different objects formed in diverse stellar environments. Such discoveries go far beyond purely academic knowledge. They greatly expand our understanding of the processes of planet and body formation occurring throughout the galaxy. The spectroscopic signatures recorded by the James Webb Space Telescope provide direct evidence of the types of chemical processing of matter in surrounding stellar systems. What is particularly significant is that the high ratio of carbon dioxide to water, observed in the Triolus comet and other similar objects, indicates either its formation near the snow lines of protoplanetary disks, regions where frozen substances condense onto forming planets, or the radiation processing of the surface layers of these bodies over millions of years. Each of these interpretations broadens our understanding of the diversity of environments and conditions under which icy bodies form beyond our solar system. These chemical discoveries have implications far beyond comet studies, as they help astronomers better understand how volatile substances vary among objects formed in different stellar systems, which in turn refines models of planetary formation and evolution. Thus, every new observation and analysis contributes to a deeper understanding of the processes that create cosmic bodies and opens new horizons in our comprehension of the universe. In the context of searching for habitable worlds beyond our solar system, scientists employ various methods and criteria to determine where and when in the galaxy conditions capable of supporting life, similar to that which we know might exist. This process involves studying numerous factors, among which the presence of environments rich in carbon dioxide is particularly important, as such conditions could have been widespread during certain epochs of galactic evolution. Understanding how these environments have changed over time helps identify the most likely locations and periods when suitable conditions for the emergence and development of life could have arisen on planets. Consequently, our perception of potentially habitable planets largely depends on knowledge of the chemical composition of their surrounding environments and their evolutionary changes in space. The scientific community's responses to the challenges associated with mapping such conditions have been vividly demonstrated through an initiative known as the Third Atlas. This large-scale project showcased the exceptional effectiveness of modern astronomical coordination efforts, especially in situations where phenomena previously seemed unattainable or impossible to observe. During the research, a unique cosmic object was discovered, resulting from the coordinated efforts of numerous institutions. The Center for Small Planets, a key element of this collaboration, organized global campaigns for meticulous tracking and data collection. In addition, space telescopes such as Hubble and James Webb provided detailed follow-up observations, enabling scientists to study the discovered object with high precision and depth. Ground-based observatories around the world made significant contributions, expanding and refining the data obtained. All of this took place within a timeframe that just a few decades ago would have seemed unattainable, demonstrating significant progress in the fields of astronomy and observational technology. Such coordinated efforts go far beyond merely utilizing advanced technologies. They embody the philosophical stance of the scientific community, rooted in the belief in the necessity of collaborative knowledge-seeking and open exchange of results. In particular, one of the key solutions was the creation of standardized astronomical archives and databases accessible to the entire world. These resources reflect a deep conviction that cosmic discoveries belong to all humanity, rather than being confined to the narrow interests of individual national institutions or governments. This openness becomes especially crucial when it comes to studying objects that could, in principle, become our first direct contacts with phenomena beyond earthly experience and conventional understanding. The transparency maintained during the implementation of the Third Atlas serves as an example of how the most unusual and complex discoveries could be processed and approached in the future. If astronomers ultimately discover truly anomalous objects that challenge our conventional understanding of physical processes, an open practice of data sharing and joint analysis will be the most reliable approach. Such a strategy will not only help distinguish genuine cosmic mysteries from possible observational errors or technological artifacts but also enable a deeper and more comprehensive understanding of new phenomena. The public attention attracted by the Third Atlas demonstrated both the potential and the difficulties of communicating complex scientific ideas to a broad audience in today's media environment. Scientific institutions and reputable organizations generally succeeded in conveying information about the unusual properties of the discovered object and its natural nature. At the same time, they acknowledged uncertainties, avoiding unwarranted speculation and exaggeration, which helped maintain public trust and interest. Thanks to these efforts, millions of people gained insights into interstellar objects, galaxy structures, comet science, and the methods used to study cosmic phenomena beyond our visible universe. However, the same channels that facilitated the popularization of scientific knowledge and the development of science education also served as platforms for spreading misinformation and conspiracy theories. Such false information can distort public perception and understanding. This approach serves as an example for future scientific research, especially when encountering discoveries that raise even more questions and complicate communication between scientists and society. In the modern world, thanks to the development of the Internet, the creation of websites with real-time event tracking capabilities, and the active work of mass media, including press conferences and educational resources, recent astronomical discoveries have become significantly more accessible to the general public. Enthusiasts of science have also contributed to observing celestial objects. Student projects based on analyzing publicly available data allowed young researchers and enthusiasts to participate in scientific investigations, while citizen science initiatives attracted thousands of volunteers worldwide to monitor the brightness, behavior, and characteristics of celestial bodies. This democratization of astronomy and scientific research in general has become one of the most inspiring trends of our time, demonstrating that scientific knowledge is increasingly becoming accessible and a collective effort. Discussions and speculations around the hypothetical third version of a hypothetical object called ITLAS, in which we participated during our research, serve not only as entertainment but also as an important scientific practice. These scenarios explore unusual and sometimes exotic possibilities, prompting scientists to pay closer attention to what distinguishes natural cosmic phenomena from potentially artificial ones. At the same time, such hypotheses stimulate the development of observational tests and experiments that can either disprove or confirm various interpretations of the observed data. These reflections remind us that the universe still holds many surprises capable of challenging our current understanding of nature and the laws of cosmos. However, the true value of such speculation lies not in its sensationalism but in its ability to stimulate scientific thinking and the search for evidence. In other words, the scenarios we consider only gain genuine significance when they generate testable hypotheses or reveal gaps in our knowledge. Otherwise, they risk turning into harmful myths or sources of unfounded fears about potential cosmic threats. The subtle distinction between scientific speculation and serious scientific work is a fundamental principle we have strived to uphold throughout this research. It reflects a broader approach that defines the development of knowledge and methods that society should follow when facing uncertainty. Science advances through the continuous interaction between hypothesis formulation and rigorous testing, between creative assumptions and disciplined evaluation of evidence. The investigation of the hypothetical object ITLAS serves as an excellent example of how this process is implemented in practice when studying truly unique and unprecedented phenomena. The history of understanding this object, from its initial discovery to detailed analysis, demonstrates how scientific knowledge evolves over time and how, step by step, confident conclusions about its nature are gradually formed. The first observations raised numerous questions due to the object's unusual properties. Subsequent measurements and studies allowed for a refinement of its composition and behavior, and ultimately, the accumulated data proved sufficient to confirm it is an ancient, chemically unique, yet predominantly natural comet. This transition from uncertainty to understanding is a vivid testament to the power of the scientific method, its patience, and meticulousness. It shows that even the most mysterious phenomena can be comprehended if approached with proper diligence and methodological rigor. Such a path offers hope and optimism regarding our ability to understand even more complex, and potentially more exotic, cosmic objects that may present themselves in the future. As our observational tools improve, the range of information we can gather expands, and opportunities for new discoveries become increasingly broad. As a result, we can anticipate the emergence of new mysteries that will require our careful and responsible study, confidently looking forward to the future with optimism. The prospects for future discoveries in astronomy are becoming ever brighter and more promising, especially as we begin to consider the place of the so-called 3 Atlas within the expanding catalog of interstellar objects that continually enrich our understanding of the universe. As part of the Legacy Survey of Space and Time, conducted by Vera Rubin Observatory, hundreds of similar interstellar objects are expected to be discovered within the next decade. These discoveries will transform interstellar bodies from rare and unusual phenomena into quite common objects for astronomical research, fundamentally changing our approach to studying space. The statistical database obtained from such a large-scale survey will allow us to significantly deepen our knowledge of the population characteristics of these objects, their chemical compositions, and dynamic properties, since currently we observe only a small fraction of their diversity due to limited sampling. Each new discovery will add new pieces to the vast puzzle related to the history of galactic evolution, planet formation processes, and the distribution of materials in interstellar space. Particularly important are the chemical signatures inherent to the 3 Atlas, They may serve as evidence of the conditions under which certain types of stars and interstellar objects form. At the same time, these signatures could remain unique, rare examples of exotic matter processing that occurs only under specific circumstances characteristic of particular regions of the galaxy or certain stages of its development. Modern technological capabilities, including sensitive broadband surveys, rapid and precise follow-up observations, as well as the development of space spectroscopy and global coordination networks, continue to advance at an impressive pace. All of this allows us to hope that future interstellar visitors will be discovered much earlier, their properties more fully characterized, and their nature understood more quickly than is currently the case. Such progress instills confidence that even the most unusual and anomalous objects will not go unnoticed. They will be recognized and studied with maximum efficiency. The broader context of space exploration created by the three atlases extends far beyond specific cases and objects. Each discovered interstellar object becomes not only an individual phenomenon but also a vital link in a chain that broadens our understanding of the material and processes occurring within the galaxy. These objects can serve as direct samples, test specimens that allow us to study the composition and properties of interstellar media, as well as the processes involved in star and planet formation. They complement indirect data obtained through spectral analysis of stars and theoretical modeling, enabling the creation of more accurate and comprehensive pictures of the cosmos. An important aspect is that these interstellar bodies act as cosmic messengers, carrying information about environments and conditions that may have existed in the galaxy long before our solar system formed. They serve as a kind of historical record, evidence of epochs and processes that are not accessible through direct observation but can be inferred from the chemical and physical states of these objects. The philosophical and conceptual implications of studying such interstellar bodies deserve special attention and recognition alongside their scientific value. The three atlases allow us to feel connected to the deep history of our galaxy, to the processes that occurred long before the formation of our solar system, and to the conditions that created the materials rushing past our cosmic threshold. This comparison provides us with valuable insight into our place within the grand scheme of cosmic evolution, into the continuity of physical processes occurring across vast scales of space and time. As we approach the completion of our study of the three atlases and its implications, the main theme that becomes increasingly apparent is a successful scientific discovery based on rigorous evidence and careful analysis. The most pessimistic scenario that motivated our research was the hypothesis of a potential catastrophe looming over our planet as a result of sudden cosmic disaster or an unexpected invasion by extraterrestrial beings. This hypothesis seemed so terrifying and inevitable that it compelled us to carefully examine its validity. However, as we studied and analyzed it thoroughly, we discovered that such fears were unfounded, and that reality is much more subtle, elegant, and even more astonishing than any initial fears suggested. Ultimately, instead of fierce concerns about a potential catastrophe, we found within ourselves an understanding that proved to be no less powerful, and perhaps even more valuable. This journey from fear to knowledge opened new horizons for us, and perhaps the most important gift that any space explorer can offer is the demonstration that patient observation, continuous study, and collaborative efforts can uncover even the most complex secrets of the universe. Part 15. Good night, Space Messenger. While the three Atlas spacecraft continue their ancient journey far from our Sun, they slowly drift away, disappearing beyond the limits of visibility into the dark expanses of interstellar space from where they once emerged. These remarkable objects, left behind after their departure, will remain in memory and records much longer than their carriers themselves, because even after their physical presence vanishes, images and traces of their existence will continue to persist in our observations and scientific data. On the cosmic horizon, amidst endless starry expanses, we can observe magnificent portraits created by the Hubble telescope. These images show blurred, star-like points surrounded by delicate shells of carbon dioxide, resembling a cosmic Christmas ornament hanging against the infinite blackness of space. In the infrared spectrum, thanks to specialized instruments, we see the molecular signatures of this comet, faint words in an ancient chemical language that an extraterrestrial visitor carries from its home planet orbiting another star. The trajectories of these objects tell their own unique story of cosmic choreography. They move smoothly and erratically, following precise laws of celestial mechanics, which can be represented in diagrams and charts. These trajectories depict the path of the three Atlas spacecraft through our solar system, passing by Mars' orbit, around the Sun at perihelion, then returning to the gas giants and continuing their journey into interstellar space. These routes are not chaos or randomness but manifestations of absolute precision and predictability that surpass human understanding. Unlike the chaos of human affairs, political and economic events, celestial bodies follow laws that have governed their motion since the very birth of the universe. These laws control the movement of planets, asteroids, and comets with such accuracy that their trajectories can be predicted with impeccable reliability. This is the deep and quiet beauty of cosmic predictability, which operates beyond human influence and control, reminding us of the eternal laws of nature. In this harmony, in this unchanging cosmic reliability, lies a certain special harmony that brings profound satisfaction and a sense of order in the vast expanse of the universe. This predictability is not merely a mathematical abstraction, it is the answer to the central question of our research. What could be the worst-case scenario? Surprisingly, it turned out to be extremely ordinary and almost cloudless. No Hollywood catastrophe capable of destroying all humanity is foreseeable in the near future. No alien invasion threatening to wipe out our civilization looms on the horizon. No cosmic upheaval capable of altering Earth's orbit or climate is imminent. But to regard this outcome as simply mundane is to miss its true significance and deeper meaning. For it is precisely the fact that we are able to predict the behavior of objects that may have existed for billions of years, formed in the cores of stars we have never even suspected, and carry chemical traces from environments we have never directly studied. That is one of the greatest achievements of science in history. These laws of physics manifest with such precise and consistent regularity that phenomena separated by vast cosmic distances, as well as by differences in time, still obey the same fundamental rules. The strangeness uncovered by the third atlas is no less astonishing than its natural origin. Its rich chemical composition, high in carbon dioxide, challenges our long-held notions of typical cometary compositions. Expanding the horizons of our understanding, it shows that materials capable of forming in various stellar environments can differ significantly in their chemical and physical makeup. The discovery that this body likely originated in dense regions of the galactic disk suggests that its origin is linked to stellar environments markedly different from those near our local galactic neighborhood. Such a fact provides a unique opportunity to study ancient galactic chemistry preserved in these objects, allowing us to trace in minute detail the evolution of materials that form stars and planets. These unusual properties have already influenced modern astronomers' ideas about planet formation, comet development, and the chemical diversity of interstellar bodies. Articles and studies dedicated to these discoveries will be cited and discussed in scientific circles for many decades, as their lessons and conclusions are integrated into broader theoretical models of how icy bodies form and evolve throughout our galaxy. The significance of this data extends far beyond the study of a single object. It illuminates the processes occurring around countless distant stars, broadening our understanding of the universe as a whole. The speculations we considered during this research, hypotheses about extraterrestrial technologies, ancient civilizations, or exotic physics, have served their purpose by stimulating our imagination and encouraging us to ask new questions. They have helped highlight the mysteries we face when exploring the true secrets of the cosmos. However, all the data obtained consistently point toward natural explanations, which, despite their astonishing nature, fit within our current understanding of physical laws. This outcome should not disappoint or upset us. After all, the universe has proven to be sufficiently strange and wondrous precisely because of natural processes, from quantum mechanics and the formation of black holes to the acceleration of cosmic expansion. All of this indicates that even adding artificial intelligence or exotic technologies to an already incredible reality may be unnecessary to experience genuine awe and expand our cosmic horizons. The most important thing is to preserve in our hearts a sense of wonder and curiosity that drives scientific exploration. The music that could accompany our farewell to this study should be neither ominous nor triumphant, but rather contemplative. Its role is to convey the mystery hidden within cosmic phenomena, while also providing clarity and understanding of these processes. Perhaps these will be compositions reminiscent of musical canvases, either for string instruments or orchestras, evoking the vastness of space while maintaining a human emotional response. The tone of such music should invite reflection, awakening feelings of wonder and admiration, rather than excitement or fear. It is in this way, with a sense of inner harmony and respect for the universe's secrets, that we should perceive its ongoing mystery and beauty. Throughout this research, we deliberately aimed to establish clear and distinct boundaries between fundamentally established scientific knowledge and areas where imagination and speculation reign, often quite distant from objective facts. In moments when our data was exhausted and theoretical assumptions and hypotheses began, we made sure to mark this with particular care and transparency. This approach allowed our viewers and readers to easily distinguish between information confirmed and based on reliable sources and ideas or fantasies that remain only assumptions and require further investigation. This clarity and transparency in conveying information reflect not only our honesty as researchers committed to scientific ethics but also the practical necessity in the modern era, when misinformation can spread much faster than fact-checking and scientific rebuttals. Ultimately, the main message derived from our research is not directly related to threats of potential collisions or scenarios of extraterrestrial invasions. Instead, it draws attention to a more subtle and perhaps more dangerous issue: the so-called space anxiety syndrome, a fear that arises in individuals confronted with phenomena beyond their current understanding and scientific knowledge. This fear, often triggered by misunderstanding or unreliable information, can generate unwarranted worries and anxieties that hinder rational perception of cosmic discoveries. In this context, three key approaches: patient observation, in-depth analysis, and international collaboration among scientists and experts, have proven effective in dismantling such fears. Only through joint efforts, pooling resources and knowledge, can humanity overcome the barriers of the unknown and achieve a clearer understanding of cosmic phenomena. In this process, not only the scientific community but also the entire global public play a vital role, as broad and open dissemination of information creates conditions for calm acceptance of new data and minimizes anxious reactions. As epilogue titles that could conclude our documentary or scientific report, attention should be drawn to the wealth of available sources of information that made this research possible. Official pages of organizations such as NASA or the European Space Agency publish authoritative summaries of observation and research results based on the latest data. Archives of institutions like the Space Telescope Science Institute store and provide factual images and spectra obtained through unique instruments such as the Hubble and James Webb telescopes, significantly expanding our scientific understanding. Professional journals and popular astronomy publications offer both in-depth technical analysis and accessible explanations intended for a broad audience. These resources are not merely bibliographies or lists of sources but a living embodiment of the democratic spirit that has accompanied the development of astronomy from its earliest days. The decision to make all observational data publicly accessible through standard astronomical archives reflects a fundamental philosophy of openness and knowledge sharing that transcends national borders and institutional limitations. This approach fosters hope that in the future, humanity will be able to handle even more unusual and complex cosmic discoveries. The promise of new interstellar objects and travelers adds a special mood to our expectations and anticipation, for each new discovery is not only another lesson about the structure and chemical composition of galaxies but also a window into the future where interstellar travel will become a reality. The observatory, named Rubin, will detect dozens of similar objects in the coming years, each opening new horizons for exploration. These objects will provide valuable information about the chemical makeup of interstellar spaces, the processes of planet formation, and the populations of wanderers, interstellar travelers who may fill the voids between star systems. Some of these objects could prove to be chemically even more unusual. Expressions of gratitude to the observatories, archives, and individual researchers, whose efforts made this extensive investigation possible, go beyond simple formal acknowledgments. These words remind us that great scientific discoveries rarely arise from the exceptional genius of a single individual or the work of one scientist. More often, they are the result of collaborative efforts, coordination, and the pooling of resources from entire institutional structures created for the study of the cosmos. It is precisely thanks to the coordinated work of ground-based observatories, space telescopes, and data archives that we were able to quickly and accurately characterize this interstellar visitor passing through our solar system. This example of modern astronomical cooperation vividly demonstrates how united efforts enable achievements that are unattainable when working in isolation. As the three atlases disappear into the vastness of the universe, carrying with them the momentum gained over 1 billion years of interstellar travel, they leave behind not only valuable scientific data and published research but also a symbol of how human society approaches the unknown world of space, with tools rather than weapons, with genuine curiosity rather than fear, with a willingness to cooperate rather than compete. This choice reflects our highest aspirations, to engage with the mysteries of the universe based on understanding and respect, not fear. And although this interstellar traveler disappears beyond the horizon, its departure does not leave emptiness. It generates anticipation, hope, and confidence that the next envoy of space is already on its way. Such a messenger will surely arrive, bearing chemical signatures from distant star systems, presenting challenges to our understanding, and offering new opportunities to expand our knowledge of the universe that gave us life. In this anticipation, in the continuous observation of the night sky, one of the most encouraging aspects of our relationship with space is revealed. Perhaps that is the very essence of our hopes, the belief that there is always something even more astonishing to discover, that questions outnumber answers, and that stars are an inexhaustible source of mysteries and inspiration. The gentle disappearance of this cosmic traveler into the depths of the night is like the fading of light, the end of one episode in our visual journey through the vast expanses of the universe. When it slips behind the starry backdrop, it no longer stands out as a separate object. It becomes part of the overall cosmic landscape, from which it has only briefly emerged. Its passage through our solar system is merely a fleeting moment within the scale of geological epochs, and its journey began billions of years ago and will continue for just as long. We are fortunate to witness this unique moment, observing this ancient interstellar wanderer, studying it, and adding its story to the growing catalog of cosmic wonders filling the space between stars. Good night, our cosmic messenger. Thank you for the lessons, for the reminders that the universe is far more astonishing and mysterious than our earthly imagination can conceive. We wish you luck on your ongoing journey through the galaxy, carrying with you any chemical secrets and ancient memories hidden within your core. You are a witness to the conditions that formed stars long before our world knew the warmth of its own sun, and this testimony remains a living reminder of the infinite mysteries of space yet to be uncovered. Until we come face to face with your kin, whose origins link them to distant systems, to those representatives of ancient epochs that existed long before our time, or to the inhabitants of those mysterious corners of the cosmic desert that surround our humble, yet wondrous and unique planetary home.